Hi there, and a heartfelt welcome. I'm so happy you've joined me today. Before we dive in, I'd love it if you could share in the comments where in the world you're tuning in from and what time it happens to be for you right now. It's always so special to see our little community connecting across time zones. A gentle thank you as well to everyone who has already subscribed and shown love with likes on the videos. It truly makes a difference. And if you have ideas or topics you'd like me to cover, please let me know in the comments. With that, let's get started. Chapter 1. Understanding Quantum Superposition Basics. Quantum superposition is a concept that invites us to imagine a world where possibilities intertwine, creating a rich landscape of potential outcomes. At its core, quantum superposition means that a particle can exist in multiple states or locations at once, until it is observed or measured. Picture a spinning coin, hovering between heads and tails, embodying both results simultaneously until it lands. This principle challenges our classical understanding of reality, where entities seem to occupy only one state at a time. To comprehend how we arrived at this intriguing notion, we must journey back through the annals of science, to a time when the foundations of quantum mechanics were just beginning to take shape. The late 19th and early 20th centuries marked a period of profound discovery. Physicists were grappling with the behavior of light and matter, seeking explanations for phenomena that classical physics could not account for. Max Planck, often regarded as the father of quantum theory, introduced the idea of quantization in the early 1900s. He proposed that energy is emitted or absorbed in discrete units, or quanta, rather than in a continuous flow. This revolutionary idea paved the way for a deeper understanding of atomic and subatomic behavior. As we delve deeper into history, we encounter Albert Einstein, who, despite his contributions to the theory of relativity, also made significant strides in quantum mechanics. His famous thought experiment, involving a particle's dual nature as both a wave and a particle, laid the groundwork for the idea of superposition. Einstein once remarked, "God does not play dice with the universe," expressing his discomfort with the inherent randomness of quantum mechanics. Yet, this randomness is what gives rise to superposition, allowing particles to inhabit multiple states simultaneously. Further illuminating the concept of superposition are key experiments that have shaped our understanding. Take the double-slit experiment, for instance, which has puzzled and fascinated scientists for generations. When particles such as electrons are fired at a barrier with two slits, they create an interference pattern on a screen behind the barrier, much like waves interacting with one another. This outcome suggests that each particle passes through both slits at once, exhibiting superposition. It is only when an observer attempts to measure which slit the particle goes through that the wave-like behavior collapses into a definite state, either one slit or the other. Imagine standing before a shimmering pond. As you toss a stone into the water, ripples cascade outward, overlapping and creating a beautiful pattern. This interaction mirrors how particles behave in superposition, creating a vibrant array of possibilities that only solidify upon observation. In the realm of quantum mechanics, we also encounter the influential figure of Niels Bohr, whose contributions further elucidated the principles of superposition. Bohr embraced the idea of wave-particle duality, and famously stated, "There are no phenomena that can be described as the motion of particles alone." His perspective emphasized that understanding quantum mechanics necessitates embracing the dual nature of reality, where particles can exist in a state of superposition until measured. As we traverse this fascinating landscape, we must also consider the concept of entanglement, which closely relates to superposition. When two particles become entangled, the state of one instantaneously influences the state of the other, regardless of the distance separating them. This phenomenon raises profound questions about the nature of reality itself, challenging our notions of locality and causality. The interplay between superposition and entanglement invites us to ponder the fundamental nature of the universe. Are we merely observers in a grand cosmic play, or do we actively shape the outcomes of these quantum states? Further exploration into these mysteries beckons us to consider how they may unravel the very fabric of existence. Throughout history, many luminaries have contributed to the evolution of these ideas. Richard Feynman, a brilliant physicist known for his ability to simplify complex concepts, once stated, "The imagination of nature is far, far greater than the imagination of man." This sentiment reflects the ever-expanding frontier of quantum mechanics, where our understanding continues to evolve as we probe deeper into the nature of superposition and its implications. As we contemplate the implications of quantum superposition, we are left with a sense of wonder and curiosity. The world of quantum mechanics invites us to embrace uncertainty, to recognize that reality is not as straightforward as it seems. Instead, it is a complex interplay of possibilities, where particles exist in a state of superposition, waiting for the gentle nudge of observation to shape their fate. Imagine standing at the edge of a vast ocean, its surface shimmering under the golden rays of the sun. Each wave represents a potential outcome, undulating and shifting, embodying the essence of superposition. Just as the ocean holds countless mysteries, so too does the quantum realm, inviting us to explore its depths with awe and reverence. As we move forward in our exploration of quantum mechanics, we will uncover more layers of this intricate tapestry. The journey through the world of superposition is not merely an academic endeavor. It is an invitation to expand our understanding of reality itself. Each discovery leads us deeper into the heart of the universe, where the boundaries of knowledge blur and the dance of possibility unfolds. The exploration of quantum superposition is enriched by a series of pivotal experiments that have shaped our understanding of the quantum world. Each experiment adds another brushstroke to the intricate portrait of reality, revealing layers of complexity that challenge our intuitive grasp of the universe. One such experiment is the quantum eraser experiment, which elegantly illustrates the nuances of superposition and measurement. Imagine a scenario where a particle, having traversed two paths, is sent through a device that can determine its route. If the route is measured, the particle behaves like a classical entity, manifesting in a definitive state. However, if the measurement is erased, the particle reverts to its wave-like nature, allowing for the possibility of interference. This phenomenon raises tantalizing questions. What does it mean for reality when our active observation can alter the state of a particle? As we contemplate these questions, we are reminded of the words of physicist John Archibald Wheeler, who famously proposed the concept of it from bit. He suggested that information is fundamental to the fabric of reality, and that each measurement we take influences the state of the universe. Wheeler's perspective encourages us to view the universe not merely as a collection of particles, but as an intricate web of information and possibilities. Another significant experiment that underscores the principles of superposition is the Bell's theorem experiments. Named after physicist John Bell, these experiments test the predictions of quantum mechanics against those of classical physics. They reveal that particles can exhibit correlations that defy classical explanations, suggesting that superposition and entanglement are deeply intertwined. This realization invites us to ponder the very nature of reality. Are particles truly independent, or are they interconnected in ways that transcend our conventional understanding? As we journey through these groundbreaking experiments, we must also acknowledge the legacy of those who have shaped the field of quantum mechanics. One such figure is Erwin Schrödinger, whose namesake equation describes how quantum states evolve over time. Schrödinger famously illustrated superposition with his thought experiment involving a cat that exists in a state of both life and death until observed. This paradox challenges us to grapple with the implications of superposition on our understanding of existence itself. What does it mean for life and consciousness if reality is predicated on observation? The contributions of Wolfgang Pauli, another towering figure in quantum mechanics, further illuminate the discourse surrounding superposition. Pauli's exclusion principle, which states that no two fermions can occupy the same quantum state simultaneously, adds depth to our understanding of particle behavior. His insights remind us that even within the realm of superposition, there are rules governing how particles interact and coexist, forming the underlying structure of matter itself. In the quest to grasp quantum superposition, we find ourselves drawn toward the concept of decoherence. This phenomenon explains how quantum systems transition from superposition to classical states, often as a result of their interaction with the environment. Imagine a delicate butterfly emerging from its chrysalis, its vibrant wings unfurling to reveal the beauty of a distinct form. Decoherence acts as a transformative process, allowing quantum potential to solidify into the reality we perceive. As we ponder these concepts, we are encouraged to visualize the delicate balance between the quantum and classical worlds. Picture a fine mist that shrouds a landscape, where every droplet represents a potential state waiting to be realized. As time unfolds, the mist begins to clear, revealing a vivid panorama. This transition reflects the journey from superposition to observation, where the myriad possibilities crystallize into the tangible world around us. In our contemplation of these ideas, we cannot overlook the significance of technological advancements that have arisen from our understanding of quantum mechanics. The development of quantum computers, which harness the principles of superposition and entanglement, stands as a testament to the power of this knowledge. These devices operate on qubits, which can exist in multiple states simultaneously, allowing for unprecedented computational capabilities. Imagine the potential to solve complex problems in mere moments, revolutionizing fields ranging from cryptography to drug discovery. As we stand at the precipice of quantum exploration, we are reminded of the words of physicist Albert Michelson, who once said, "The most important thing is to have a good and open mind." This mindset is vital as we delve deeper into the mysteries of superposition and its implications. The universe beckons us to explore, to embrace uncertainty, and to remain open to the wonders that lie ahead. In this tranquil journey through the landscape of quantum mechanics, we find ourselves captivated by the interplay of possibility and reality. Each step forward reveals new dimensions of understanding, urging us to question, to imagine, and to dream. What awaits us beyond the threshold of observation? What secrets does the universe hold, waiting for our curious minds to uncover them? As we continue to peel back the layers of quantum superposition, the tapestry of knowledge expands, inviting us to venture further into the depths of existence. Each discovery not only enriches our comprehension of the cosmos, but also deepens our connection to the very nature of reality itself. The journey is as profound as it is beautiful, a harmonious exploration of the intricate dance between possibility and observation, inviting us to reflect on our place within this vast and wondrous universe. As we immerse ourselves further into the contours of quantum superposition, we encounter the profound implications of this principle, not only for physics but for our understanding of reality itself. The idea that particles can exist in multiple states simultaneously invites us to reconsider the very nature of existence. Are we merely passive observers, or do our perceptions and measurements play an active role in shaping the universe around us? To illustrate this concept more vividly, consider the thought experiment known as Schrödinger's cat. This hypothetical scenario, devised by Erwin Schrödinger, presents a cat in a sealed box alongside a radioactive atom and a Geiger counter. If the atom decays, the counter triggers a mechanism that releases poison, resulting in the cat's demise. Until observed, the cat is considered to be both alive and dead, encapsulating the essence of superposition. This paradox challenges us to confront the complexities of observation and reality. What does it mean for a creature's fate to hinge upon an act of observation? This inquiry into the implications of superposition leads us to the concept of observer effect, a cornerstone in quantum mechanics. The very act of measuring a quantum system alters its state, collapsing the superposition into a single outcome. Imagine a delicate flower swaying in the breeze, its petals shimmering in the sunlight. As you reach out to touch it, the gentle motion ceases, and the flower settles into a stillness. This moment of observation transforms potential into actuality, reflecting how our interactions with the quantum world yield definitive results from a myriad of possibilities. As we traverse this realm, we must also acknowledge the contributions of contemporary scientists who continue to expand our understanding of quantum mechanics. One such figure is Alain Aspect, whose experiments in the early 1980s provided compelling evidence for the phenomenon of entanglement. Aspect's work illuminated the intricate connections between particles, reinforcing the idea that the universe is not merely a collection of isolated entities, but an interconnected web of relationships. His findings resonate with the notion that superposition and entanglement are intertwined, threading through the fabric of reality. What does it mean for our understanding of the universe when particles can influence one another instantaneously, regardless of distance? Such questions challenge our classical intuitions and invite us to explore the philosophical implications of quantum mechanics. Are we living in a deterministic universe, or does quantum uncertainty govern the very fabric of existence? In contemplating these questions, one cannot help but be drawn to the thoughts of physicist David Bohm, who proposed a holistic view of the universe, suggesting that everything is interconnected and that separateness is an illusion. Bohm's ideas resonate with the principles of superposition and entanglement, inviting us to view reality as a unified whole rather than a fragmented collection of parts. Can we embrace this interconnectedness in our daily lives, recognizing the unseen threads that bind us to one another and the universe? As we reflect upon these concepts, we are led to consider the potential applications of quantum superposition in technology. Quantum computers, fueled by the principles of superposition and entanglement, promise to revolutionize our computational capabilities. Imagine a future where complex problems, once thought insurmountable, are solved in the blink of an eye. This technology could redefine industries, from medicine to artificial intelligence, as we harness the power of the quantum realm to complement our understanding of the classical world. Yet, amidst these advancements, we must remember the delicate nature of the quantum state. Just as a fragile butterfly is susceptible to the slightest disturbance, so too are qubits vulnerable to environmental noise and decoherence. The challenge lies in preserving the quantum state long enough to harness its potential. This intricate balance between maintaining superposition and achieving practical outcomes invites us to explore innovative solutions, blending creativity with scientific inquiry. As we journey through the landscape of quantum mechanics, we are reminded of the words of physicist Richard Feynman: "If you think you understand quantum mechanics, you don't understand quantum mechanics." This playful acknowledgement of the complexity of the quantum world encourages us to embrace the unknown, to remain curious and open-minded. The mysteries of superposition beckon us to venture deeper, challenging our perceptions and expanding our horizons. In this serene exploration of quantum superposition, we find ourselves at the intersection of science and philosophy, where the boundaries blur and new frontiers emerge. The principles we uncover not only illuminate the workings of the universe, but also mirror our own experiences of uncertainty, possibility, and transformation. Imagine standing in a tranquil forest, surrounded by towering trees reaching for the sky. Each tree represents a potential outcome, a pathway branching into myriad directions. As you wander through the woods, you encounter the beauty of choice, where each decision leads to a different destination. This metaphor reflects the essence of superposition, where countless possibilities coexist, waiting for our conscious choice to manifest them into reality. As we advance through the chapters of quantum mechanics, let us carry with us the sense of wonder and curiosity that fuels our exploration. The journey through superposition is not merely an academic pursuit. It is an invitation to reflect on the nature of existence and our place within this vast and intricate cosmos. What lies beyond the veil of observation? What new insights await us as we continue to probe the depths of quantum reality? The answers may lead us to not only understand the universe, but also to uncover the profound connections that bind us to it. Chapter 2: The Science Behind Quantum States. The world of quantum states unfolds like a delicate fabric woven with the threads of possibility and uncertainty. At its essence, a quantum state is a mathematical description of a physical system, encapsulating all the information about a particle's properties. Imagine a painter mixing colors on a palette, each hue representing a different aspect of the particle's existence, its position, momentum, spin, and energy. In this vibrant realm, particles are not mere points of matter, but rather manifestations of potential, veiled in the mystery of quantum mechanics. To grasp the elegance of quantum states, it is essential to distinguish them from classical states. In classical physics, we encounter objects that exist in a definitive state. An apple rests on a table, a car moves along a road, each with a certain position and velocity. These entities adhere to predictable laws, allowing us to chart their paths with accuracy. However, when we venture into the quantum domain, we find that the rules shift dramatically. A particle is not confined to a single position or state. Instead, it dances between possibilities, embodying a spectrum of potential outcomes. Imagine a photon, the fundamental particle of light. In the classical world, we might say it travels in a straight line, illuminating the space around it. Yet in the quantum realm, this photon occupies a quantum state that allows it to be in multiple places at once, akin to a faint whisper echoing across a vast canyon. Its behavior is governed by probabilities, and only when we measure it do we force it to choose a specific path, much like a dreamer awakening from slumber, suddenly aware of the choices before them. This notion of occupying multiple states simultaneously is best captured by the principle of superposition. Picture a serene lake, undisturbed, reflecting the sky above. In this tranquil setting, the water can be thought of as a superposition of all possible states of the lake, calm, rippling, or even turbulent, until something disturbs its surface. Similarly, a quantum particle exists in a superposition of states, each with its own probability. It is only when we perform a measurement that the particle collapses into one of these states, much like the lake, settling into a single reflection. The brilliance of this concept is supported by a robust mathematical framework, primarily established through the work of physicists like Schrödinger and Dirac. Schrödinger's wave equation, a cornerstone of quantum mechanics, describes how the quantum state of a system evolves over time. This equation is akin to a symphony, with each note representing the various possibilities that compose the melody of a particle's existence. The wave function, a solution to this equation, encapsulates all the potential outcomes, providing a profound glimpse into the nature of reality. Consider the wave function as a cosmic map, guiding us through the labyrinth of quantum states. It encodes not only the position of a particle, but also the likelihood of finding it in various locations at any moment. The beauty lies in the wave function's ability to interfere with itself, creating patterns of probability that govern the behavior of particles. This interference can be illustrated through the famous double-slit experiment, where particles, such as electrons, pass through two slits simultaneously, creating an interference pattern on a screen. This phenomenon exemplifies how particles can exist in a state of superposition, demonstrating that they can behave like waves, spreading out and overlapping, only to reveal their true nature upon observation. As we continue to explore the depths of quantum states, we encounter the concept of entanglement. Imagine two particles intertwined in a cosmic embrace. When one is measured, the state of the other instantaneously reflects this change, regardless of the distance between them. Einstein referred to this phenomenon as spooky action at a distance, marveling at how entangled particles defy classical intuitions about locality. This remarkable property has profound implications for our understanding of the universe, suggesting that at a fundamental level, everything is interconnected. The mathematical elegance of quantum mechanics does not merely reside in its equations. It also allows us to harness these principles in innovative ways. This brings us to the burgeoning field of quantum computing, where the principles of superposition and entanglement are employed to solve complex problems at unprecedented speeds. Quantum bits, or qubits, can exist in multiple states simultaneously, allowing them to process vast amounts of information concurrently. Imagine a library with countless books, where each book represents a different state of information. In the quantum realm, a single qubit can represent an entire shelf of books, enabling calculations that would take classical computers eons to accomplish. Yet, despite the allure of quantum computing, the journey into the realm of quantum states is not without its challenges. The delicate nature of superposition makes quantum systems susceptible to disturbances from their environment, leading to a phenomenon known as decoherence. This occurs when a quantum system interacts with its surroundings, causing it to lose its coherent state and behave more classically. The challenge for researchers lies in preserving the fragile quantum states long enough to perform meaningful computations or experiments. The stories of notable physicists who have contributed to our understanding of quantum states are remarkable. Niels Bohr, a key figure in the development of quantum theory, famously stated, "We are not able to grasp the real essence of atomic objects, but we can describe their behavior with great precision." This acknowledgement of the limitations of human understanding resonates deeply within the quantum realm, where the more we learn, the more we realize how much remains shrouded in mystery. As we peer into the intricacies of quantum states, we must also contemplate the philosophical implications of these phenomena. What does it mean for reality if particles can exist in multiple states? How does our observation influence the very fabric of the universe? These questions invite us to reflect on the nature of existence itself, blurring the lines between observer and observed. In the heart of this exploration lies the concept of potentiality. Every quantum state embodies a realm of possibilities, waiting to be realized. Imagine standing before an artist's canvas, each brushstroke representing a different outcome. The painting is not complete until the artist chooses which colors to blend and where to place each stroke. Similarly, the universe unfolds its potential in a symphony of quantum states, each moment an opportunity for creation and discovery. As we continue to immerse ourselves in this captivating world, the properties of quantum states remind us of the complexity of existence. The dance of particles, the interplay of probabilities, and the intricate mathematical frameworks all converge to create a reality that is as wondrous as it is perplexing. Each revelation invites us to ponder the nature of our universe and our place within it, urging us to remain open to the mysteries that lie ahead. The properties of quantum states extend beyond mere existence. They embody a symphony of behavior that defies our classical intuition. Take, for instance, the dual nature of particles. At times, they behave like discrete particles, localized in space, while at other moments they manifest as waves, spreading across a region like gentle ripples on a pond. This wave-particle duality is one of the cornerstones of quantum mechanics, illustrating how particles can transcend traditional definitions. Imagine a serene beach at dawn. The gentle waves lap against the shore, each crest a reminder of the ocean's vastness. Yet, beneath the surface, countless grains of sand lay in quiet repose, each one a potential particle, each one a quantum state. Just as the waves can take on different forms depending on the wind and tide, so too can particles shift between wave-like and particle-like behavior depending on how we observe them. This fluidity invites us to explore the underlying principles of quantum mechanics, revealing a world where certainty is replaced by a tapestry of probabilities. The idea of superposition is not just an abstraction. It is a fundamental aspect of how we understand these particles and their interactions. Each quantum state is a blend of possibilities, each one contributing to the overall behavior of the system. When we measure a particle, we force it to select one of these possibilities, collapsing the wave function into a single outcome. This moment of measurement is akin to an artist deciding the final brushstroke on a canvas. Until that moment, the painting is alive with potential, a myriad of interpretations awaiting realization. Central to the discussion of quantum states is the mathematical framework that supports these ideas. The mathematics of quantum mechanics allows us to express and manipulate wave functions with precision. When we delve into the realm of linear algebra, we encounter vectors and matrices that elegantly describe the relationships between different quantum states. Each state can be represented as a vector in a complex space, where the rules of addition and multiplication unfold in ways that are both familiar and alien. Consider the insight of Richard Feynman, who famously remarked, "The most important thing is to keep the most important thing the most important thing." This wisdom resonates within the mathematical structures of quantum states, emphasizing the importance of understanding the fundamental elements that govern their behavior. The interplay of these mathematical constructs helps physicists predict and analyze outcomes, crafting a narrative where abstract numbers and symbols unveil the mysteries of the universe. The exploration of quantum states also leads us to the concept of quantum interference. When particles occupy a superposition of states, their wave functions can interfere with one another, leading to patterns of constructive and destructive interference. This phenomenon is not merely an esoteric curiosity. It is the driving force behind many technologies we encounter today. Imagine the intricate designs created by ripples in water, merging and parting, forming beautiful patterns that shift with each wave. Similarly, quantum interference shapes the probabilities of where a particle might be found, guiding us to profound insights about the nature of reality. One of the most compelling aspects of quantum mechanics is how it challenges our understanding of determinism. In classical physics, the behavior of an object can be predicted with certainty if we know its initial conditions. However, in the quantum world, uncertainty reigns supreme. The Heisenberg uncertainty principle states that we cannot simultaneously know both the position and momentum of a particle with absolute precision. This inherent limitation invites us to embrace a world where probabilities govern existence, where outcomes are dictated not by certainties but by likelihoods. As we journey deeper into the realm of quantum states, we encounter the concept of decoherence once more. This phenomenon plays a pivotal role in understanding how quantum systems transition to classical behavior. When a quantum particle interacts with its environment, it becomes entangled with the surrounding cosmos, leading to the loss of its delicate superposition. Picture a delicate butterfly that flits through a sunlit garden, its wings shimmering in the light. As it brushes against a flower, the essence of its quantum state becomes entangled with the vibrant colors of the petals, forever altering its trajectory. In this way, decoherence illustrates the fragility of quantum states, reminding us that the delicate balance between possibility and reality can easily be disrupted. The journey through quantum states is not merely a scientific endeavor, it is an invitation to ponder the very essence of existence. What does it mean to exist in a world governed by probabilities? How do our observations shape the universe around us? These profound questions reverberate through the annals of quantum mechanics, urging us to reflect on our role as observers within this intricate web of reality. As we contemplate the implications of quantum states, we are drawn to the stories of those who have ventured into this enigmatic territory. The work of physicists like John Bell, who proposed Bell's theorem, challenged our understanding of locality and entanglement, igniting debates about the nature of reality itself. Bell's insights not only reshaped quantum mechanics, but also invited us to reconsider the philosophical underpinnings of our universe. His words echo through time. If you want to make a real experiment, you have to make a choice. In this vast playground of quantum mechanics, every choice we make, every measurement we perform, resonates with the potential to unlock new dimensions of understanding. The interplay of quantum states, their superpositions and entanglements, invites us to embrace the unknown. As we stand on the threshold of discovery, we are reminded that the universe is filled with mysteries waiting to be unraveled. With each revelation, we come closer to embracing the beauty and complexity of quantum states. They serve as a reminder that reality is not merely a collection of isolated events, but a rich, interconnected tapestry of possibilities. As we continue to explore this captivating landscape, we find ourselves not just observers, but participants in a grand cosmic symphony, where the notes of quantum states resonate with the heartbeat of the universe itself. Chapter 3. The Role of Observation in Quantum Mechanics. In the intricate world of quantum mechanics, the act of measurement takes on a significance that transcends simple observation. It becomes a transformative force, reshaping the very essence of reality. When we measure a quantum system, we are not merely extracting information, we are influencing the system itself. This interplay between observer and observed is what defines the quantum realm, ushering us into a deeper understanding of phenomena that defy our classical intuitions. Imagine a small particle, a photon or an electron, existing in a cloud of potentialities, akin to a painter's palette filled with vibrant colors. Each hue represents a different state, and until we observe the particle, it remains an exquisite blend of possibilities. This notion is at the heart of quantum measurement, where we encounter the concept of the observer effect. When an observer takes a measurement, they identify a specific state among many, collapsing the myriad possibilities into a singular reality. This act of observation is not passive, it actively shapes the universe around us. The implications of the observer effect ripple through the fabric of quantum mechanics. It suggests that reality is not a fixed entity waiting to be discovered, but rather a dynamic interplay of possibilities that are brought into focus by our actions. This idea prompts us to ponder a profound question: is the universe inherently deterministic, or is it a canvas upon which we, as observers, paint our reality? As we ponder this, we find ourselves confronting the uncertainty that lies at the very heart of quantum physics. The phenomenon known as wave function collapse encapsulates this concept beautifully. Prior to observation, a quantum system is described by a wave function, a mathematical entity that encodes the probabilities of finding a particle in various states. Picture this wave function as a swirling mist enveloping the particle in a multitude of potential outcomes. However, once we decide to measure the system, this mist dissipates, and the particle adopts a definite state. It is as if we are peeling back the layers of possibility to reveal a singular truth. This collapse is not merely a theoretical abstraction. It is a fundamental aspect of how quantum systems interact with the world around them. To illustrate the nuances of this process, we can turn to thought experiments that have captivated the minds of physicists for generations. One of the most famous is Schrödinger's cat, a paradoxical scenario proposed by the Austrian physicist Erwin Schrödinger in the early 20th century. In this thought experiment, a cat is placed inside a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, leading to the cat's demise. Until the box is opened, the cat exists in a state of superposition, both alive and dead, simultaneously. This striking imagery invites us to reflect on the consequences of measurement. The cat's fate is intertwined with the act of observation itself. Once the box is opened and the observer looks inside, the wave function collapses, and reality solidifies into one of two outcomes. The cat is either alive or dead, but not both. This paradox highlights the peculiar nature of quantum mechanics, where the line between observer and observed blurs, and where reality seems to hinge upon our choices. Schrödinger, in his exploration of these concepts, famously remarked, "I do not like it, and I want to know what it is." His discomfort with the implications of quantum mechanics reveals the tension inherent in grappling with a world that defies classical logic. The observer effect and wave function collapse challenge our understanding of existence, urging us to reconsider the role of consciousness in shaping reality. As we move deeper into the realm of quantum mechanics, we encounter a landscape where certainty dissolves into ambiguity and where the act of observation brings forth a myriad of questions. What does it mean for the universe if our observations can alter the very fabric of reality? How does our consciousness, as observers, intertwine with the cosmos to create the world we experience? This interplay between observation and reality is not merely a philosophical inquiry, it has practical implications in the realm of quantum technology. Quantum computing, for example, harnesses the principles of superposition and entanglement, allowing for the processing of information in ways previously thought impossible. In these systems, the act of measurement takes on a new meaning, as qubits exist in a state of superposition until they are observed. This allows quantum computers to solve complex problems with astonishing speed, showcasing the power of observation in a practical context. As we reflect on these themes, we can visualize the quantum world as a vast ocean with waves of possibility crashing against the shores of our understanding. Each observation we make is like a pebble cast into this ocean, creating ripples that alter the course of events. The observer effect serves as a reminder that our interactions with the universe are not merely passive. They shape the very outcomes we seek to comprehend. In the world of quantum mechanics, the observer is not just a passive witness. They are an active participant in the unfolding narrative of existence. The implications of this realization extend beyond the confines of physics, inviting us to explore the relationship between consciousness and reality itself. What if our thoughts, our intentions, could influence the outcomes we observe? This question invites contemplation of the interconnectedness of all things, urging us to consider the profound impact of our perceptions on the world around us. As we navigate this wondrous landscape of quantum mechanics, we find ourselves standing at the intersection of science and philosophy. The observer effect and wave function collapse challenge us to reconsider the nature of existence, suggesting that reality is not a static entity, but a vibrant, ever-changing tapestry woven from our interactions. This realization opens the door to a deeper understanding of our place in the cosmos, inviting us to embrace the mysteries that lie beyond the veil of perception. In this exploration, we are reminded of the words of Albert Einstein: "Reality is merely an illusion, albeit a very persistent one." His insights resonate through the ages, urging us to question the very nature of our reality. As we delve into the intricacies of measurement and observation, we find ourselves embracing the unknown, welcoming the uncertainties that lie ahead. The journey through the quantum realm is a journey of discovery, where each observation is a stepping stone toward greater understanding. The very act of measurement transforms the landscape of possibilities, reshaping our perceptions and deepening our connection to the universe. As we continue to explore the role of observation in quantum mechanics, we invite you to imagine the myriad possibilities that await, each one a reflection of the dynamic interplay between observer and observed. As we traverse further into the realm of quantum mechanics, the notion of measurement becomes even more intriguing when we consider the implications of the observer effect. It is not merely an abstract concept. It serves as a reminder that the act of observation is woven into the very fabric of reality. Can we truly separate ourselves from the universe we seek to understand? The answer appears to be a resounding no. Our interactions with quantum systems are not just passive observations. They play an essential role in defining the outcomes we experience. The observer effect becomes particularly poignant when we consider the duality of light. Light can behave as both a wave and a particle, a phenomenon known as wave-particle duality. Imagine a beam of light passing through a narrow slit. When unobserved, it creates an interference pattern on a screen, suggesting that each photon behaves as a wave, existing in multiple states simultaneously. However, when we attempt to measure which slit the photon travels through, the interference pattern vanishes, replaced by a pattern indicative of particles. This transition from wave-like behavior to particle-like behavior occurs solely because of our observation. It raises profound questions about the nature of reality. Does light choose its behavior based on our act of measurement? What does this imply about the fundamental nature of existence? Renowned physicist Niels Bohr, a pioneer in the understanding of quantum mechanics, articulated this relationship beautifully when he stated, "There is no quantum world. There is only an atomic world." His assertion underscores the idea that what we perceive as reality is deeply intertwined with our observations and interpretations. The essence of the quantum realm is one of interconnectedness, where the observer is an integral part of the observational process. As we contemplate these concepts, it is essential to explore the collapse of the wave function in greater depth. When an observation occurs, the wave function, which encompasses all potential states of a system, collapses into a singular outcome. This collapse is not a physical process we can observe directly. Rather, it is a mathematical transformation that reveals the state of the system at the moment of measurement. Imagine a vast library filled with books, each representing a possible state of a quantum system. When no one is reading, the stories remain open to interpretation, their potential infinite. Yet, as soon as a reader selects a book, the narrative solidifies into a specific tale, embodying one reality over all others. The implications of this collapse are far-reaching. It suggests that the universe is not merely a collection of predetermined events unfolding in a linear sequence. Instead, it is a realm of possibilities, where potential outcomes coexist until we introduce our consciousness. As physicist Eugene Wigner eloquently expressed, "The laws of quantum mechanics do not say that the observer has to be a conscious being. They only require that the observer is a physical system." This notion invites us to ponder the role of consciousness in shaping our reality, blurring the lines between observer and observed. In contemplating the role of observation, we inevitably arrive at thought experiments that have shaped our understanding. Schrödinger's cat remains a cornerstone of this inquiry, but it is not the only one. The double-slit experiment, another iconic demonstration, challenges our perceptions of reality in equally fascinating ways. It illustrates how the act of measurement alters the behavior of particles, compelling us to confront the very nature of existence. Imagine a world where particles dance between states, only to be swayed by the gentle touch of observation. What does it mean for our understanding of reality if mere observation can shape the behavior of these particles? The double-slit experiment illustrates the dual nature of light and matter, revealing that everything exists in a state of potential until we decide to observe it. This realization ignites a sense of wonder and curiosity. Each observation we make sends ripples through the quantum fabric, continuously redefining the boundaries of what is possible. Are we, in essence, co-creators of our reality, shaping the universe with our thoughts and actions? As we reflect on the interconnectedness of observation and reality, we can draw inspiration from the words of physicist David Bohm, who remarked, "The observer is not separate from the observed." This insight reverberates through the corridors of quantum mechanics, reminding us that we are part of a larger whole, intricately woven into the cosmic tapestry. Our observations do not exist in isolation. They resonate with the universe, crafting a symphony of existence that echoes through time and space. As we immerse ourselves in these ideas, it becomes clear that the role of observation in quantum mechanics is a gateway to deeper understanding. It invites us to consider our place in the cosmos, urging us to recognize our agency in shaping the unfolding narrative. With each observation, we participate in the creation of reality, forging connections that transcend the boundaries of time and space. In the quiet moments of contemplation, we may find ourselves reflecting on the implications of these insights. What lies beyond our perception? How do our observations weave together the myriad strands of existence? In this exploration of quantum mechanics, we are not merely passive observers. We are active participants in a grand cosmic play, where each role is vital to the unfolding story of the universe. As we continue to navigate this fascinating terrain, we are beckoned to embrace the uncertainties that lie ahead. The interplay of observation and reality invites us to remain curious, ever eager to explore the mysteries that await us. Each inquiry leads us deeper into the heart of the quantum realm, illuminating the paths we have yet to tread. The journey is one of discovery, where the act of observation serves as a reminder of our profound connection to the universe, inviting us to inquire, to learn, and to marvel at the intricate dance of existence. In this wondrous exploration of quantum mechanics, the observer effect and the collapse of the wave function remind us that reality is not a singular, unchanging entity. It is a vibrant, ever-evolving landscape shaped by our actions and perceptions. As we press forward, we carry with us the knowledge that each observation contributes to the intricate web of existence, and within that web lies the potential for infinite possibilities awaiting our discovery. Chapter 4: Implications of Quantum Superposition in Computing. In the realm of quantum computing, superposition takes on a transformative role, illuminating pathways that classical computing could only dream of traversing. Imagine a vast, shimmering sea of possibilities, where each wave represents a different outcome, and each ripple signifies an interaction. This is the essence of superposition, the idea that quantum bits, or qubits, can exist in multiple states simultaneously. Qubits are the fundamental building blocks of quantum information. Unlike classical bits, which hold a value of either 0 or 1, qubits can embody both values at the same time. Picture a spinning coin again, but this time envision it not merely hovering between heads and tails, but rather as a vibrant orb brimming with potential. This is the power of superposition at work, allowing qubits to explore a multitude of configurations in parallel. When we harness this property, we unlock vast computational power, capable of solving complex problems far more efficiently than our traditional counterparts. Consider the implications of this dual existence. In classical computing, a bit is like a solitary traveler, navigating a linear path from one destination to another, each step methodical and predictable. In contrast, qubits journey through a labyrinth of possibilities, allowing quantum computers to evaluate numerous solutions at once. This parallelism is not just a minor enhancement. It fundamentally alters the landscape of computing and opens new frontiers in various fields, from cryptography to materials science. The contrast between classical bits and qubits extends beyond mere functionality. It delves into the very nature of information itself. While a classical bit is confined to a binary choice, qubits thrive in a realm of superposition, where they can represent a combination of states. This ability leads to exponential growth in computational capacity as more qubits are entangled together. Entanglement, another cornerstone of quantum mechanics, weaves a deeper connection between qubits, allowing them to influence each other instantaneously, regardless of distance. Imagine two dancers moving in perfect harmony, where the motion of one dictates the rhythm of the other. This interconnectedness amplifies the power of superposition and enables quantum computers to work on problems in ways that classical computers cannot replicate. As we delve into the world of quantum algorithms, we find that they are designed to leverage the unique capabilities of superposition. Quantum algorithms can process vast amounts of data simultaneously, utilizing the inherent parallelism of qubits. For instance, consider Shor's algorithm, which harnesses superposition to factor large numbers efficiently. In our classical world, factoring can be a time-consuming endeavor, especially as the numbers grow larger. Yet, with quantum superposition, the algorithm explores multiple factors at once, reducing the time required to solve these complex equations significantly. Imagine how this could reshape industries reliant on secure communications. Cryptography, which currently underpins the security of our digital world, could face a revolution. As physicist Michio Kaku once said, quantum computers will be able to crack most of the codes currently in use. With the power of superposition, quantum computers could potentially unlock encrypted data that classical systems would take millennia to decrypt. In addition to cryptography, quantum computing's implications stretch into optimization problems, where the ability to evaluate countless possibilities simultaneously can lead to breakthroughs in logistics, finance, and even drug discovery. Picture a vast city where delivery routes are optimized for efficiency, reducing costs and time. Quantum algorithms can evaluate all possible routes in the blink of an eye, identifying the most efficient path and transforming industries in the process. However, it is essential to recognize the challenges that accompany these advancements. The delicate nature of qubits makes them susceptible to errors and decoherence, where environmental factors disrupt their superposition state. Researchers and engineers are diligently working on error correction techniques and building more stable qubits to ensure the reliability of quantum computations. The pursuit of fault-tolerant quantum computing is akin to nurturing a fragile seedling in a storm, requiring patience and resilience to thrive. As we explore the implications of quantum superposition in computing, we begin to understand that this is not merely an academic exercise. It represents a profound shift in our approach to technology and problem-solving. The potential to revolutionize industries and enhance our understanding of complex systems is within our grasp. The journey toward fully harnessing quantum computing is still unfolding, filled with challenges and opportunities alike. In this ever-evolving landscape, the pioneers of quantum computing remind us of the importance of curiosity and innovation. Figures like Richard Feynman, who once expressed, "If you think you understand quantum mechanics, you don't understand quantum mechanics," invite us to embrace the mystery and complexity that lies ahead. With each step forward, we inch closer to unlocking the full potential of superposition and its transformative impact on our world. As we continue to explore the depths of quantum computing, we find ourselves on the brink of a new technological era. The implications of superposition transcend mere computation. They challenge our understanding of reality itself. What does it mean to possess the ability to explore countless outcomes simultaneously? How might this reshape our interactions with technology and the universe at large? These questions linger in the air like the gentle whisper of wind through the trees, inviting us to ponder the possibilities. As we stand at the crossroads of classical and quantum worlds, we discover a landscape rich with potential, waiting for the curious minds willing to unravel its mysteries. The journey is not merely about the technology we build, but about the insights we gain as we navigate this uncharted territory together. Quantum algorithms designed to exploit the unique attributes of superposition offer a glimpse into the potential future of computation. They are not merely iterations of classical algorithms, but represent an entirely different paradigm. For instance, Grover's algorithm exemplifies this shift. It allows for the searching of unsorted databases in a time that is quadratically faster than any classical counterpart. Imagine a vast library where each book represents a piece of information. In a classical world, you would sift through each title one by one, a cumbersome endeavor. However, with Grover's algorithm, you can essentially open multiple books at once, uncovering the desired information with remarkable efficiency. This exponential speedup is made possible by the principles of superposition and entanglement, which allow quantum computers to evaluate many possibilities simultaneously. The merging of qubits into intricate networks enables a quantum computer to perform numerous calculations in parallel, dramatically enhancing computational capability. It is akin to a symphony where each instrument plays a note harmoniously, creating a rich and complex auditory experience that would be impossible with a single instrument playing alone. The potential applications of quantum algorithms extend far beyond mere computational speed. In fields such as machine learning, quantum computing could transform the way we analyze data. By leveraging superposition, quantum algorithms can uncover patterns and insights within datasets that are too vast and intricate for classical systems to decipher. Imagine training a machine learning model that can adapt and learn from countless variations of data points simultaneously, leading to quicker and more accurate predictions. This could revolutionize industries ranging from finance to healthcare, where timely and precise decision-making can have profound implications. However, the journey into the realm of quantum algorithms is not without its challenges. The intricacies of designing and implementing these algorithms require a deep understanding of quantum mechanics and advanced mathematical frameworks. Researchers are continually exploring new techniques to optimize algorithms, ensuring they can run efficiently on quantum hardware, which is still in its developmental stages. The task is reminiscent of early computer programmers who had to navigate the limitations of their machines, innovating solutions that would lay the groundwork for the digital age. As we ponder the implications of these advancements, we must also consider the ethical dimensions of quantum computing. With great power comes great responsibility. The ability to crack encryption algorithms poses significant risks, especially in an age where data privacy is paramount. The prospect of quantum computers breaching security systems raises questions about the integrity of our digital landscape. How can we prepare for a future where traditional methods of encryption may become obsolete? In this context, researchers are already working on quantum-resistant cryptographic techniques, which aim to create security measures that can withstand the computational prowess of quantum systems. This proactive approach underscores the necessity of balancing innovation with caution, ensuring that as we unlock the potential of quantum computing, we also safeguard the very fabric of our interconnected world. The narrative of quantum computing is still being written, with each new discovery illuminating the path forward. The pioneers of this field, such as David Deutsch, who proposed the concept of a universal quantum computer, remind us that we are at the forefront of a new frontier. The ultimate aim of science is to explain the universe in a way that makes it comprehensible, Deutsch asserts. This quest for understanding is what drives researchers and enthusiasts alike as they explore the depths of quantum phenomena. As we consider the implications of superposition in quantum computing, we are invited to envision a future where the boundaries of possibility expand. The intersection of quantum mechanics and information technology challenges our perceptions and inspires a sense of wonder. What if we could solve complex mathematical problems that currently elude us? What if we could simulate molecular interactions to discover new materials or drugs with precision? These questions ignite our imagination and compel us to explore the uncharted territories of science. In this landscape, the role of collaboration becomes paramount. Quantum computing is not a solitary endeavor. It thrives on the collective wisdom of researchers, engineers, and visionaries from diverse fields. By fostering collaboration across disciplines, we can accelerate progress and harness the full potential of quantum technologies. This interconnectedness mirrors the entangled qubits themselves, where each element contributes to the overarching system, enhancing its capabilities. The beauty of quantum superposition lies not only in its ability to compute, but also in its power to inspire new ways of thinking. As we traverse this fascinating terrain, we are reminded of the words of physicist Niels Bohr, who said, "We are not only the progeny of the universe, we are the universe's way of understanding itself." This profound insight encapsulates the essence of our journey into quantum computing, inviting us to reflect on our place within the cosmos as we strive to unravel its mysteries. As we stand on the precipice of this new era, the implications of quantum superposition in computing beckon us to explore further. The stories of the past, the innovations of the present, and the possibilities of the future converge, creating a rich narrative that invites us to participate. What new discoveries await us as we continue to push the boundaries of human understanding? The answers lie ahead, waiting for the curious minds willing to question, explore, and innovate. Chapter 5: Quantum Superposition in quantum entanglement. Quantum entanglement is a phenomenon that transcends the boundaries of classical physics, inviting us into a world where particles become intimately connected, regardless of the distance that separates them. Imagine two entangled particles, like twin stars in a vast cosmos, sharing a bond that defies the conventional understanding of space and time. Their states are intertwined in such a way that the measurement of one instantly influences the state of the other, a remarkable connection that Albert Einstein famously referred to as spooky action at a distance. This enigmatic relationship is deeply rooted in the concept of quantum superposition, where particles exist in multiple states simultaneously. To comprehend quantum entanglement fully, we must first revisit the essence of superposition. In our previous explorations, we envisioned particles as vibrant expressions of potential, each existing in a multitude of states until observed. Similarly, entangled particles embody this principle, their correlated states a manifestation of superposition. Picture a pair of dice, rolled together, where the outcome of one die is inextricably linked to the other. Until they land, each die holds numerous possibilities, yet once they are observed, a clear correlation emerges, revealing the delicate dance of chance and certainty. Entangled particles exhibit a remarkable property. Their states are correlated in such a way that measuring one instantly determines the state of the other. This correlation persists even when the particles are separated by vast distances. Imagine two entangled photons, one sent to a distant observer while the other remains with you. When you measure the polarization of your photon, the instant results will reveal the polarization state of the distant photon, regardless of the space that intervenes. This phenomenon challenges our intuitive notions of locality and causality, suggesting a deeper interconnectedness within the quantum realm. Experiments have vividly demonstrated the reality of entanglement and superposition. One of the most renowned experiments is the Bell test, named after physicist John Bell, who formulated a theorem that provided a way to test the predictions of quantum mechanics against classical theories. In these experiments, pairs of entangled photons are produced and sent to two separate detectors. As the measurements are made, the results consistently align with the predictions of quantum mechanics, showcasing the strong correlations between the entangled particles. Imagine the thrill of witnessing the unbreakable bond between these particles, revealing a symphony of probabilities that classical physics could never have predicted. Moreover, the implications of quantum entanglement extend beyond mere curiosity. They hold profound potential for practical applications, particularly in the fields of quantum communication and cryptography. In a world increasingly reliant on secure data transmission, the principles of entanglement offer a means to achieve truly secure communication channels. Quantum key distribution, for instance, utilizes entangled particles to create cryptographic keys that are inherently secure. When one party measures their particle, any attempt by an eavesdropper to intercept the communication introduces detectable disturbances, alerting the parties involved to potential breaches. Imagine a world where your private conversations remain genuinely private, shielded by the very laws of nature. The concept of quantum entanglement also fuels the development of quantum networks, where information can be transmitted instantaneously across vast distances. Picture a network of entangled particles linking cities around the globe, facilitating communication that is not only rapid but also unassailable. Such advancements promise to revolutionize industries, from finance to healthcare, by ensuring that sensitive information remains secure and protected from prying eyes. Building upon these ideas, we can appreciate the profound implications that quantum entanglement and superposition hold for our understanding of reality. They challenge our perceptions of separateness, urging us to reconsider the fabric of existence itself. With every new discovery, we inch closer to unveiling the mysteries of the quantum world, where particles dance together in an intricate ballet of possibilities, whispering secrets of connection and unity that resonate through the cosmos. As we continue to explore this enthralling landscape, it becomes clear that the journey into quantum entanglement is not merely an academic pursuit. It is an invitation to rethink the very nature of our universe. What does it mean for two particles to be connected across the vastness of space? How does this interconnection inform our understanding of reality? And what might it teach us about the nature of consciousness itself? The quest for knowledge in quantum mechanics is a testament to humanity's enduring curiosity and desire to understand the universe. As Richard Feynman once remarked, the most important thing is not to stop questioning. This spirit of inquiry drives scientists to unravel the complexities of quantum entanglement and superposition, leading to discoveries that may redefine our understanding of existence. Each experiment, each observation, builds upon the foundation laid by those who came before, revealing a path illuminated by the light of knowledge. In this ongoing exploration, we find ourselves at the cusp of a new era, where the mysteries of the quantum realm beckon us forward. The dance of entangled particles continues, whispering the secrets of connectivity and the limitless potential of the universe. As we gaze into the depths of this quantum ocean, we are reminded that the boundaries of knowledge are ever expanding, inviting us to dive deeper into the unknown. The voyage into quantum entanglement and superposition is a journey of discovery, an odyssey that promises to unveil the wonders of existence itself. The interplay of quantum entanglement and superposition opens a door to a realm of communication that is as revolutionary as it is mysterious. Imagine the potential of a quantum internet woven from the very threads of entangled particles. Such a network could operate on principles that defy classical limitations, allowing instantaneous data transfer not bound by the constraints of traditional technologies. This vision of the future is not merely speculative. It is being actively pursued by researchers worldwide, aiming to harness the power of quantum mechanics for practical applications. One of the most significant developments in this area is quantum teleportation, a process that allows the transfer of quantum states from one particle to another without the particles themselves moving through space. This phenomenon relies heavily on entanglement, where two particles share a linked state. By performing a specific measurement on one of the entangled particles, its state can be transmitted to another distant particle, effectively teleporting the state. Imagine sending a message not as a physical object, but as an instantaneous transfer of information, where the original particle ceases to exist in its former state, while the new one emerges in the destination. This concept challenges our conventional understanding of communication, suggesting a future where information flows with a speed and security that transcends our current capabilities. The implications of quantum communication extend into the realm of cryptography, where the security of information becomes paramount. The foundation of quantum key distribution is built on the principles of entanglement and superposition, creating a method of encryption that is theoretically unbreakable. As we consider the vulnerabilities of classical encryption methods, which rely on complex algorithms that can be hacked by powerful computers, quantum cryptography offers a refreshing alternative. The laws of quantum mechanics guarantee that any attempt to eavesdrop on a communication channel will disturb the entangled particles, alerting the communicating parties to a breach. This aspect raises a profound question. How might our understanding of privacy and security evolve in a world where our communication is shielded by the very fabric of reality? Renowned physicist Charles Bennett, a pioneer in quantum information science, once stated, "The laws of quantum mechanics allow us to do things that classical physics cannot." His insights capture the essence of how quantum mechanics is reshaping our understanding of information transfer and security. As researchers delve deeper into the nuances of entanglement, they uncover methods to create robust quantum networks that could revolutionize industries by ensuring that sensitive information remains secure from interception. Furthermore, the exploration of entangled particles is not solely confined to communication technology. The principles of quantum entanglement have the potential to enhance measurements in various scientific fields. For example, in quantum sensing, entangled states can improve the precision of measurements, allowing scientists to detect minute changes in physical systems. Picture a sensor, enhanced by quantum entanglement, that can measure gravitational waves with unprecedented accuracy, opening new avenues in astrophysics and cosmology. Such advancements challenge our existing measurement techniques, pushing the boundaries of what is possible. As we reflect on the journey of quantum entanglement and superposition, we find ourselves at the intersection of philosophy and science. The implications of these phenomena compel us to reconsider our understanding of reality itself. What does it mean for particles to be interconnected across vast distances? Could this interconnectedness hint at a deeper, possibly shared nature of existence? The questions are as tantalizing as the answers are elusive, inviting us to ponder the fabric of the universe and our place within it. In contemplating these profound ideas, we are reminded of the words of Niels Bohr, who stated, "We are not trying to uncover the ultimate reality. We are trying to uncover the most useful descriptions of our measurements." This perspective highlights the pragmatic approach scientists take as they explore the quantum realm. Each discovery, each experiment, serves to refine our understanding of these intricate principles, guiding us toward ever deeper insights. As we venture further into this captivating world, we recognize that the journey is ongoing. The quest for knowledge in quantum mechanics is fueled by a collective curiosity, a desire to unlock the secrets of the universe. With every experiment, we peel away the layers of complexity, revealing a landscape rich with potential. Quantum entanglement and superposition do not merely challenge our existing paradigms. They invite us to embrace the unknown, to seek beauty in the intricate relationships that define the cosmos. The application of these quantum principles in real-world scenarios showcases the profound potential they hold. Take, for instance, the development of quantum-enhanced imaging techniques, where the unique properties of entangled photons can create images with unparalleled clarity. Imagine a medical imaging device that utilizes quantum entanglement to reveal details that traditional imaging techniques simply cannot capture. The ability to visualize biological processes at a quantum level could transform diagnostics and treatment methods, ushering in a new era of healthcare. In the realm of computing, quantum entanglement and superposition are paving the way for innovations that could redefine problem-solving. Quantum algorithms exploit these phenomena to tackle complex problems in optimization, simulation, and machine learning, offering solutions that were once thought to be intractable. Picture a world where quantum computers can process vast data sets with a speed and efficiency that outstrips classical computers, leading to breakthroughs in fields as diverse as climate modeling, drug discovery, and artificial intelligence. As we navigate this uncharted territory, we are reminded of the interconnectedness that permeates not only the quantum realm, but also our lives. The relationships we cultivate, the knowledge we seek, and the discoveries we make all contribute to a greater understanding of the universe. Quantum entanglement and superposition serve as metaphors for the connections we share, encouraging us to recognize the bonds that unite us in our quest for understanding. The journey through quantum mechanics is not merely a scientific endeavor. It is a reflection of our quest for meaning and connection in an intricate and often perplexing universe. Each revelation encourages us to remain curious, to question, and to explore, as we strive to decode the mysteries that lie within the quantum landscape. The dance of entangled particles, shimmering in the vast expanse of possibility, beckons us to continue our exploration, revealing a future brimming with promise and wonder. Chapter 6. Applications of Quantum Superposition in Technology. In the ever-evolving landscape of technology, the principles of quantum mechanics have begun to weave their way into practical applications, transforming our understanding of how we interact with the world around us. Imagine a world where the very fabric of reality is harnessed to improve our daily lives, where the mysterious behaviors of particles guide advancements in fields as varied as computing, sensing, and medicine. This is not a distant dream. It is the reality of quantum technologies today. Current technologies utilizing quantum principles are reshaping industries and redefining possibilities. Quantum computing, which has already captivated the imaginations of scientists and engineers, is leading the charge. By leveraging the power of qubits, these systems can process information in ways that classical computers simply cannot. They can simultaneously explore multiple solutions to complex problems, akin to a vast, interconnected web of ideas rather than a single thread. This capability holds the promise of revolutionizing fields such as cryptography, optimization, and artificial intelligence. As we move beyond computing, the realm of quantum sensors emerges as a beacon of innovation. These devices exploit the principles of quantum superposition and entanglement to achieve unprecedented levels of sensitivity. Imagine being able to detect minute changes in gravitational fields or measure magnetic fields with such precision that even the faintest signals become discernible. Quantum sensors are already making waves in fields ranging from geology, where they assist in locating natural resources, to healthcare, where they can enhance imaging techniques, allowing for clearer and more accurate diagnostics. The advancements in quantum imaging are particularly striking. Traditional imaging techniques, while effective, often encounter limitations in resolution and sensitivity. Quantum imaging, however, enables us to capture images with enhanced clarity, revealing details that were once hidden from view. Picture a medical imaging device that utilizes quantum principles to provide a clearer picture of the inner workings of the human body, allowing doctors to diagnose conditions earlier and more accurately. This not only enhances patient care, but could also lead to groundbreaking discoveries in our understanding of diseases. The implications extend into pharmaceuticals and materials science, where quantum superposition offers a new lens through which to examine the molecular world. Imagine the potential of simulating complex chemical reactions at the quantum level, allowing researchers to predict the behavior of molecules with remarkable accuracy. This could significantly accelerate the development of new drugs, paving the way for treatments that target diseases more effectively and with fewer side effects. The ability to model interactions at such a granular level transforms how we approach drug discovery, making it more efficient and targeted. In materials science, quantum principles open doors to the creation of novel materials with tailored properties. Picture a material designed at the atomic level to exhibit extraordinary strength while remaining lightweight, or one that conducts electricity with minimal resistance. These advancements could usher in a new era of technology, enabling the development of more efficient batteries, superconductors, and even new forms of renewable energy. The potential applications are as vast as the imagination itself, ranging from improved electronics to advanced construction materials. As we gaze into the future, the implications of quantum superposition for technology development are awe-inspiring. The ongoing research and experimentation in quantum technologies herald a paradigm shift that could redefine our technological landscape. We find ourselves standing at the precipice of a new era, where the boundaries of what is possible are continually pushed outward. Each breakthrough invites us to reconsider our assumptions about the universe and our place within it. What might the future hold as these technologies advance? Imagine a world where quantum computing enables instant problem-solving for global challenges, such as climate change or food scarcity. Envision a society where quantum sensors can monitor environmental changes in real time, providing critical data that informs policy decisions and conservation efforts. The fusion of quantum principles with everyday technology could enhance not only our capabilities, but also our understanding of the world. In this unfolding narrative, the contributions of outstanding individuals cannot be overlooked. Visionaries in the field, such as Richard Feynman and David Deutsch, have laid the groundwork for what we now explore. Feynman famously remarked on the power of quantum mechanics to inspire new ways of thinking, urging us to embrace the mysteries that lie ahead. Their insights continue to fuel the imaginations of researchers and technologists, inspiring innovations that harness the strange yet profound nature of quantum superposition. As we ponder these possibilities, we are reminded of the interconnectedness of all things. Each advancement in quantum technology not only propels us forward, but also raises new questions and challenges. How will we ensure that these powerful tools are used ethically and responsibly? How can we prepare for the disruptions they may bring to existing industries and societal structures? These are the inquiries that lie before us as we embark on this quantum journey, navigating the complexities of a world transformed by the very principles that govern the universe. The path ahead is illuminated by the wonders of quantum superposition, inviting us to explore, discover, and innovate. With each step forward, we inch closer to unlocking the full potential of the quantum realm, shaping a future rich with possibilities that were once confined to the realm of imagination. The applications of quantum principles are only beginning to unfold, promising a horizon filled with discoveries that will resonate through generations to come. Quantum sensors are emerging as a transformative force in a variety of fields, enabling scientists and engineers to glean insights that were once beyond our reach. These devices rely on the principles of quantum mechanics to achieve extraordinary levels of sensitivity, surpassing traditional measurement techniques. Imagine a tiny sensor capable of detecting gravitational waves, ripples in space-time caused by events like merging black holes, and providing insights into the universe's most profound mysteries. This is no longer a mere fantasy. It is a reality made possible by advancements in quantum technologies. In the realm of healthcare, quantum sensors are revolutionizing diagnostic imaging. Traditional imaging techniques, while useful, often struggle with resolution and sensitivity, limiting our ability to visualize intricate biological processes. Quantum-enhanced imaging can provide a clearer and more detailed view of the human body. Picture a quantum-based MRI that captures images with an unprecedented level of clarity, allowing for early detection of diseases such as cancer. Such advancements could lead to not only improved patient outcomes, but also a deeper understanding of the underlying mechanisms of various diseases. Moreover, in the field of environmental monitoring, quantum sensors can detect minute changes in temperature, pressure, and magnetic fields. Imagine devices that can monitor the Earth's magnetic field fluctuations with remarkable precision, providing crucial data for understanding climate change and natural disasters. This capability could empower scientists to predict geological events, aiding in disaster preparedness and response. As we delve into the potential uses of quantum technologies in pharmaceuticals and materials science, the implications become even more profound. The ability to simulate molecular interactions at the quantum level opens new avenues for drug discovery. Imagine a world where researchers can model complex chemical reactions with unparalleled accuracy, predicting how new compounds will behave in the body before they are synthesized. This not only accelerates the development of new medications, but also reduces the need for extensive trial and error processes, ultimately leading to safer and more effective treatments. In materials science, the application of quantum principles can revolutionize how we design and manufacture materials. Picture materials engineered at the atomic level, exhibiting properties that were once thought impossible. For instance, researchers are exploring superconductors that operate at room temperature, which could lead to revolutionary advancements in energy transmission and storage. This could dramatically enhance the efficiency of electrical grids and reduce energy loss, ultimately contributing to a more sustainable future. The future implications of quantum technologies extend beyond mere enhancements to existing systems. They challenge the very foundations of our technological landscape and provoke us to rethink how we approach problems across disciplines. As we stand on the brink of this quantum revolution, the question arises: how will we harness these advancements to address the pressing challenges of our time? Envision a future where quantum computers can optimize complex logistics networks, making supply chains more efficient and reducing waste. Imagine the possibilities of real-time environmental monitoring, where quantum sensors provide instant feedback on pollution levels, empowering communities to take swift action. The integration of quantum principles into our daily technologies could lead to a more informed society, equipped to tackle the multifaceted challenges that lie ahead. As we contemplate these advancements, we must also reflect on the ethical considerations they entail. The power of quantum technologies brings with it responsibilities that require careful thought. How do we ensure that these tools are used for the greater good? How can we navigate the potential disruptions they may cause to established industries and societal norms? These questions prompt us to consider not only the technological possibilities, but also the moral implications of our discoveries. In this evolving landscape, the contributions of pioneering researchers and thinkers remain crucial. Their visions and insights continue to inspire the next generation of scientists and technologists. As we explore the applications of quantum superposition in technology, we are reminded of the interconnectedness of scientific inquiry and ethical responsibility. Each innovation presents an opportunity to not only advance our understanding of the universe, but also to enhance the human experience. As we embrace the unfolding narrative of quantum technologies, we find ourselves in a unique position, one that blends curiosity with caution. The journey ahead is illuminated by the promise of discoveries that can reshape our world, inviting us to explore the uncharted territories of the quantum realm. Each step taken in this direction is a testament to our collective ambition to understand and harness the fundamental principles of nature for the betterment of humanity. In this ever-expanding frontier, the applications of quantum superposition in technology are just beginning to scratch the surface of what is possible. With each breakthrough, we inch closer to unlocking the mysteries of the quantum world, where the lines between imagination and reality blur, revealing a landscape rich with potential for innovation and discovery. The future beckons, filled with opportunities to redefine our existence and deepen our connection to the universe. As we explore the landscape of quantum technologies, the advancements in quantum sensors and imaging stand out as some of the most remarkable applications of quantum superposition. These devices are not merely incremental improvements, they represent a leap into an era where measurement is redefined. Imagine the ability to detect a magnetic field so faint that it is invisible to classical sensors, revealing hidden structures in the Earth's crust, or the subtle variations in brain activity that could lead to breakthroughs in neuroscience. Quantum sensors utilize the delicate interplay of superposition and entanglement to enhance their sensitivity, allowing us to peer into the depths of phenomena that were previously obscured. One notable advancement in quantum imaging is quantum ghost imaging, a technique that allows us to reconstruct an image of an object using correlations between light particles. This method relies on the principles of quantum mechanics to reveal details that conventional imaging methods might miss. Picture a scenario where researchers can visualize the internal structures of delicate biological samples without damaging them, leading to new insights in cellular biology and pathology. Such capabilities could transform our understanding of life at its most fundamental level, providing tools to study diseases in ways that were previously unattainable. In the pharmaceutical realm, the implications of quantum superposition are equally profound. Researchers are increasingly turning to quantum simulations to model the interactions of complex molecules, drastically reducing the time and resources needed for drug discovery. Imagine a world in which a new medication can be designed and tested in silico, predicting its efficacy and safety before it ever reaches the lab. This not only accelerates the development of life-saving drugs, but also holds the potential to tailor treatments to individual patients, ushering in a new age of personalized medicine. The integration of quantum principles into pharmaceutical research is likely to yield breakthroughs that reshape our approaches to health and disease. Materials science, too, stands to benefit significantly from quantum innovations. The ability to engineer materials at the atomic level opens a myriad of possibilities. Consider the development of materials with unique properties, such as metamaterials that can bend light in unprecedented ways, or nanoscale materials that exhibit extraordinary strength while remaining lightweight. These advancements could lead to revolutionary applications in electronics, energy storage, and even structural engineering. The potential to create materials that are not only stronger and more efficient, but also environmentally friendly, presents an exciting pathway towards sustainable technological solutions. What does the future hold as these technologies continue to evolve? The implications stretch far beyond mere enhancements in existing tools and techniques. As quantum technologies mature, They may catalyze a transformation in how we approach global challenges. Imagine a world where quantum computing enables us to model climate systems with unparalleled accuracy, providing insights that inform policy decisions and drive effective action against climate change. The integration of quantum sensors into environmental monitoring could lead to real-time assessments of air and water quality, empowering communities to respond to ecological changes swiftly and decisively. These advancements hinge not only on scientific discovery, but also on ethical considerations and societal impacts. As we harness the power of quantum technologies, we must remain vigilant about the responsibilities that come with them. How can we ensure that these innovations benefit all of humanity, rather than exacerbating existing inequities? The quest for answers to these questions is as critical as the technological advancements themselves. It is a journey that requires collaboration, foresight, and a commitment to ethical stewardship. The narrative of quantum technologies is still unfolding, inviting us to imagine a future where our relationship with the universe is transformed by the very principles that govern it. As we stand on the cusp of this exciting frontier, we are reminded that the journey into the quantum realm is not just a scientific pursuit. It is a collective endeavor that encompasses curiosity, creativity, and a deep respect for the interconnectedness of all things. Each advancement brings us closer to unlocking the mysteries of the universe, revealing a landscape rich with potential for innovation, discovery, and ultimately, a deeper understanding of our place within the cosmos. Chapter 7. Philosophical Perspectives on Quantum Superposition. In the realm of quantum mechanics, philosophical questions often bubble to the surface, beckoning us to explore the fundamental nature of reality itself. What does it mean for something to exist in multiple states at once? Can we reconcile the strange behavior of particles with our everyday understanding of existence? These inquiries invite us to ponder the very fabric of our universe, challenging our perceptions and urging us to reconsider our assumptions about the world around us. As we explore the interpretations of quantum mechanics, we find ourselves at a crossroads of thought. The Copenhagen interpretation, one of the most widely accepted frameworks, posits that quantum particles exist in a state of probability until they are measured. This view suggests that the act of observation is not merely passive but actively shapes reality, collapsing the myriad possibilities into a single outcome. Imagine standing before a vast canvas, where each stroke of the brush represents a different potential reality. It is only through the touch of the artist that the painting comes to life, revealing a singular vision amid a sea of possibilities. In stark contrast, the many worlds interpretation offers a radically different perspective. This view suggests that every measurement creates a branching of realities, where every possible outcome occurs in its own separate universe. Picture a grand tree, its branches extending infinitely in all directions, each representing a different version of reality. In this interpretation, every choice we make, every event that unfolds, leads to the creation of a new world, forever diverging from the others. This notion raises profound questions about our existence. Are we mere players in a grand cosmic play, or do we possess agency in the choices we make, with each decision creating ripples across an infinite tapestry of worlds? These interpretations delve into the heart of free will and determinism. If the Copenhagen interpretation holds true, does that imply that our choices are mere illusions, shaped by the act of measurement and observation? Or does the many worlds interpretation grant us a sense of agency, suggesting that every possibility exists concurrently, allowing us to traverse paths of our own choosing? The tension between these ideas invites us to reflect on our understanding of self and choice. Are we the authors of our own stories, or are we swept along by the currents of a predetermined fate? As we ponder the implications of quantum mechanics, our understanding of reality begins to shift. The classical view of a deterministic universe, where cause and effect govern every action, is challenged by the fluidity of quantum superposition. Imagine a world where events are not fixed, where the outcome of a situation is not predetermined, but rather exists in a state of potential. This perspective invites us to embrace uncertainty and the unknown, fostering a deeper appreciation for the complexities of existence. Renowned physicist Niels Bohr once remarked, "We must be clear that when it comes to atoms, language can be used only as in poetry." This sentiment encapsulates the essence of quantum mechanics, a field that defies our traditional linguistic constructs and demands a new way of thinking. As we grapple with the paradoxes of superposition and entanglement, we find ourselves navigating a landscape rich with metaphor and imagery, where the boundaries of science and philosophy blur. The implications of quantum mechanics extend far beyond the realm of physics, permeating our understanding of consciousness and existence. What if our perception of reality is merely a projection of our minds, shaped by the interplay of observation and measurement? The idea that our consciousness might influence the very fabric of reality is both exhilarating and unsettling. It beckons us to consider the interconnectedness of all things, a web of existence where each thought, action, and observation resonates through the cosmos. As we explore these philosophical landscapes, we cannot help but wonder about the nature of time itself. If every possibility unfolds in parallel universes, what does that mean for our linear perception of time? Does the past exist simultaneously with the present and future, each moment a mere slice of a much grander reality? This notion invites us to reimagine time not as a rigid sequence of events, but as a fluid continuum, where moments intertwine and possibilities coexist. The exploration of quantum superposition also leads us to reflect on our own existence within this intricate framework. Are we isolated beings, separate from the universe, or are we deeply intertwined with the fabric of reality? The interconnectedness suggested by quantum mechanics invites us to embrace a sense of unity, a recognition that our individual experiences are but threads in the greater tapestry of existence. As we contemplate the philosophical implications of quantum mechanics, we are beckoned to engage with the mysteries of consciousness. How does our awareness shape our reality? Can we transcend the limitations of our perceptions to glimpse the underlying truths of the universe? These questions push us beyond the confines of empirical understanding, inviting us to explore the depths of human experience and the nature of awareness itself. The journey through quantum mechanics is not merely a scientific endeavor. It is a profound exploration of what it means to be human. The remarkable discoveries in this field challenge us to confront our beliefs, to question our understanding of existence, and to embrace the wonder of the unknown. As we navigate this intricate landscape, we are reminded of the words of physicist Richard Feynman, who said, "The most important thing is not to stop questioning." This spirit of inquiry propels us forward, urging us to explore the boundaries of knowledge and to remain curious about the mysteries that lie ahead. In this quest for understanding, we find that the philosophical questions raised by quantum mechanics are not merely abstract concepts. They resonate deeply within us, inviting us to reflect on our own lives, our connections to others, and our place in the cosmos. The interplay of free will and determinism, the nature of reality, and the essence of consciousness all converge in a dance of thought, beckoning us to engage with these ideas on a personal level. As we continue to unravel the threads of quantum mechanics, we are reminded that this journey is not just about particles and waves. It is about the very nature of existence itself. The exploration of quantum superposition invites us to embrace the unknown, to question our assumptions, and to recognize the beauty in uncertainty. In doing so, we open ourselves to a world rich with possibility, a world where the boundaries of science and philosophy intertwine, revealing new dimensions of understanding. In the end, the questions raised by quantum mechanics compel us to seek a deeper connection with ourselves and the universe. They encourage us to embrace the complexities of existence, to ponder the nature of reality, and to remain ever curious in our pursuit of knowledge. As we journey through this fascinating terrain, we find that the exploration of quantum superposition is not just a scientific inquiry. It is a profound exploration of what it means to be alive in a universe full of wonder and mystery. As the threads of quantum mechanics intertwine with our philosophical inquiries, we are led to consider the implications of superposition on our understanding of reality itself. One might ask, how do these principles alter the very foundation of what we perceive as existence? The interplay of possibilities, as described by superposition, suggests a fluidity to reality that contrasts sharply with our everyday experiences, where we often encounter fixed states and clear outcomes. Imagine living in a world where every thought, every decision, and every outcome is not merely a singular occurrence, but a multitude of potentials, existing simultaneously. This mindset invites us to expand our comprehension of reality beyond the confines of classical physics, where the universe is a predictable machine, operating under strict laws of cause and effect. Instead, we step into a realm where uncertainty reigns, and possibilities flourish like wildflowers in an untamed field. This shift in perspective has profound implications for our understanding of free will. If every decision we make creates a branching path of realities, how do we reconcile this with the notion of personal agency? Are our choices genuine acts of free will, or are they simply predetermined patterns echoed through the multiverse? The many worlds interpretation embraces the notion of infinite choices, yet it also raises questions about the nature of identity. In a landscape where every decision spawns new realities, what does it mean to be you? Are you defined by the choices made in one universe, or are you an amalgamation of countless versions of yourself, each experiencing a different outcome? Philosophers and scientists alike have grappled with these concepts, seeking to understand the essence of consciousness within this quantum framework. The idea that our consciousness may play a role in shaping reality offers a tantalizing glimpse into the interconnectedness of mind and matter. If observation can collapse probabilities into a singular outcome, might our thoughts and intentions similarly influence the world around us? This question echoes the sentiments of many thinkers throughout history who have pondered the relationship between consciousness and the universe. As we consider these philosophical implications, we cannot overlook the profound impact on our comprehension of time. If every moment is a nexus of possibilities, does time itself become a fluid construct rather than a linear progression? The traditional view of time as a straight line, where past, present, and future are distinctly separated, is challenged by the notion that all moments coexist, like layers of a rich, multidimensional painting. This perspective invites us to envision time not as a relentless march forward, but as a vast landscape, where each moment can be accessed and explored. Within this intricate web of existence, we can also explore the nature of reality itself. What does it mean for something to be real in a universe where infinite realities coexist? The implications of quantum superposition extend beyond particles and waves. They touch upon our very perception of existence. Reality may not be as fixed as we once thought, but rather an ever-evolving tapestry, woven together by the threads of possibility and observation. As we delve deeper into these ideas, the thoughts of physicist David Bohm resonate. He proposed that the universe is an indivisible whole, where the apparent separateness of objects is merely an illusion. This perspective aligns beautifully with the philosophical inquiries raised by quantum mechanics, suggesting that our fragmented understanding of reality may obscure the underlying unity of existence. It invites us to view reality as a complex interplay of relationships, where every action reverberates through the fabric of the cosmos, influencing outcomes in ways we may not yet comprehend. Reflecting on the nature of our reality, one might wonder if our experiences, emotions, and connections to others could also be seen through the lens of quantum principles. The relationships we cultivate and the impacts we have on one another may be akin to entangled particles, intertwined in ways that transcend our immediate understanding. Each interaction could potentially ripple through the multitude of realities, shaping not only our personal journeys, but also the collective experience of humanity. In this exploration, we are reminded of the importance of embracing uncertainty. The quantum realm teaches us that not everything is knowable, and that ambiguity is a fundamental aspect of existence. This idea encourages a sense of humility, a recognition that our understanding is but a fraction of the greater whole. In acknowledging the limits of our perception, we open ourselves to the vastness of possibility that lies beyond. As we continue to reflect on the philosophical implications of quantum superposition, we find ourselves drawn into a deeper contemplation of existence. The questions raised by quantum mechanics do not offer easy answers. Rather, they invite us to engage with the mysteries of life and the universe. Each inquiry acts as a stepping stone, leading us toward a greater understanding of ourselves and our place within this intricate cosmic dance. Through this journey, we are encouraged to cultivate a sense of wonder, a recognition that the universe is filled with complexities that extend beyond our immediate comprehension. The exploration of quantum mechanics, with its intertwining threads of science and philosophy, invites us to remain curious and open-hearted, embracing the unknown with grace and humility. As we navigate this rich landscape, we are reminded that the pursuit of knowledge is not merely about acquiring facts, but about fostering a deeper connection with the universe and with one another. Chapter 8. The Challenges of Quantum Superposition. Achieving and maintaining quantum superposition presents a myriad of challenges that extend beyond mere theoretical constructs. These challenges are deeply rooted in the delicate nature of quantum systems, where the slightest disturbance can collapse the intricate web of possibilities that superposition embodies. Imagine a fragile glass sculpture, shimmering with light but susceptible to the faintest touch. In the quantum realm, this fragility is magnified as particles exist in a state of potential until they are disrupted by external influences. Decoherence plays a pivotal role in this narrative. It is the process by which quantum systems lose their quantum properties, transitioning into classical states as they interact with their environment. Picture a once vibrant watercolor painting slowly fading into a monochrome image, the colors blending into a uniform wash as time passes. This phenomenon occurs because quantum systems are not isolated. They are continually bombarded by their surroundings, whether it be air molecules, electromagnetic radiation, or even thermal fluctuations. Every interaction nudges the delicate balance, leading to a loss of coherence, and thus the collapse of superposition. This interplay of quantum states and their environment reveals why sustaining superposition is so intricate. Researchers liken quantum systems to a delicate balance of spinning tops, where each top represents a different state. The more tops there are, the more complex the interaction among them becomes. As they collide with one another, or with external forces, their coordinated motion falters, and they tumble toward a definitive state. The vivid potential that superposition offers is thus diminished, as decoherence strips away the richness of quantum reality. The implications of decoherence are profound, particularly in the realm of quantum computing. Here, qubits, the fundamental units of quantum information, must remain in superposition to harness their full potential. Yet, as we have discussed, these qubits are vulnerable. Imagine a symphony orchestra, where each musician must play in harmony to create a beautiful melody. If one musician falters, the entire performance can fall apart. In quantum computing, if qubits lose their coherence, the computational advantage they offer erodes, leading to errors and inefficiencies. Technological hurdles in quantum computing are not solely confined to the effects of decoherence. The physical realization of qubits themselves presents its own set of challenges. Various approaches to building qubits exist, ranging from superconducting circuits to trapped ions and topological qubits. Each method has its advantages and drawbacks, but all share the common challenge of maintaining superposition while minimizing decoherence. Imagine a race where each participant is running on a different terrain, some smooth and others rugged. The journey toward a functional quantum computer involves navigating these diverse landscapes, each requiring innovative solutions to traverse successfully. Further complicating the landscape is the necessity for error correction. In classical computing, errors can often be corrected through redundancy and checks. But in the quantum world, where states are fragile and interconnected through superposition and entanglement, error correction takes on a different form. Researchers are exploring various methods, such as surface codes and cat codes, which rely on entangled states to protect information. Picture a fortress, where the walls are constructed from intertwined vines. Each vine represents a qubit, and together they form a resilient barrier against disturbances. The challenge lies in constructing these fortifications without compromising the delicate balance of superposition. Ongoing research is a beacon of hope against these challenges. Scientists and engineers are tirelessly exploring new materials, techniques, and theoretical frameworks to enhance the stability of qubits and prolong their coherence times. Recent advancements in topological qubits, for example, offer the promise of greater resilience to decoherence by exploiting exotic particles that exhibit unique properties under certain conditions. Imagine a rare flower that blooms in the harshest of climates, thriving where others wither. This pursuit embodies the spirit of innovation in the quantum realm, where researchers strive to cultivate robustness amid fragility. As we journey through this landscape of quantum challenges, it becomes evident that the path forward is not merely a linear progression, but rather a complex interplay of ideas and discoveries. Collaboration across disciplines, from physics to materials science, is vital as researchers pool their knowledge to tackle these formidable obstacles. The collective efforts of brilliant minds have already yielded promising results, showcasing the resilience of human ingenuity in the face of daunting challenges. What does the future hold for quantum superposition? Will we find ways to shield qubits from decoherence, allowing them to flourish in their potential? Or will new discoveries shift our understanding of quantum mechanics entirely? These questions linger in the air, inviting us to imagine a world where the challenges of quantum superposition are met with creativity and perseverance. Each research breakthrough, each innovative solution, brings us one step closer to unlocking the full power of quantum computing and the mysteries of the universe itself. The quest to maintain quantum superposition and combat decoherence is a path laden with both intellectual and practical challenges. One significant hurdle arises from the very nature of quantum systems, which are universally sensitive to their environments. This sensitivity leads us to consider the implications of temperature fluctuations. Imagine a serene lake, its still surface disturbed by the tiniest gust of wind. In the quantum realm, even the faintest thermal vibrations can precipitate a collapse of superposition, as particles interact with heat and ambient energy, losing their delicate quantum coherence. Research has shown that maintaining low temperatures can enhance the stability of qubits, enabling them to hold onto their quantum states longer. However, achieving and sustaining these low temperatures requires sophisticated cooling technologies, such as dilution refrigerators. These ingenious machines operate on principles of thermodynamics to reach temperatures close to absolute zero, where thermal noise is minimized. Picture a world where the air is still and crisp, allowing the particles to dance freely without the interference of heat, thus preserving their quantum nature. Moreover, the architecture and design of quantum systems pose unique challenges. For instance, superconducting qubits are built using materials that can conduct electricity without resistance, a property that allows for prolonged coherence times. Yet, even these advanced materials can be plagued by noise from electromagnetic fields, which can disrupt their delicate states. Researchers are exploring various shielding techniques and novel materials to mitigate these effects. Imagine a protective cocoon woven from threads of advanced technology, carefully shielding qubits from disruptive forces, allowing them to flourish in their quantum states. The fascinating interplay between quantum systems and their environments has led scientists to delve deeper into the field of quantum error correction. Unlike classical error correction, which relies on redundancy, quantum error correction must carefully navigate the entangled nature of qubits. Innovations, such as the surface code and the quantum repeaters, serve as the backbone of this ongoing research. These methods resemble an intricate tapestry, where each thread is essential to the integrity of the whole, ensuring that even when disturbances occur, information can be preserved and recovered. As we extend our gaze beyond the current challenges, the potential of topological qubits emerges as a beacon of hope. These qubits are constructed from exotic particles known as anyons, which maintain their quantum states in a more robust manner. Imagine a rare gem, resilient and shimmering, capable of withstanding the trials of time and environment. Topological qubits promise to offer that resilience, potentially allowing for longer coherence times and reduced susceptibility to decoherence. This could revolutionize quantum computing, paving the way for more stable and efficient systems, capable of performing complex calculations that classical computers can only dream of. Ongoing research in quantum computing is a testament to the collaborative spirit of the scientific community. Teams of physicists, computer scientists, and engineers are coming together, pooling their diverse expertise to tackle these formidable challenges. This synergy fuels innovation, as researchers share insights and breakthroughs, collectively pushing the boundaries of what is possible. Each discovery adds another layer of understanding, much like a masterful painting that reveals new details upon closer inspection. The quest to conquer decoherence and maintain superposition is not merely a technical endeavor, but a philosophical journey as well. What does it mean for a qubit to exist in multiple states while simultaneously being influenced by its surroundings? Each step forward in this field compels us to reassess our understanding of reality itself. The principles of quantum mechanics challenge our classical intuitions, reshaping our perceptions of existence. How do we reconcile the fragile nature of quantum states with the pursuit of stability in our technological aspirations? As we ponder these questions, it becomes clear that the solutions to the challenges of quantum superposition are not solely found in the laboratory. They require a reimagining of our scientific approaches, encouraging us to think beyond conventional frameworks. The creativity of the human mind, intertwined with the relentless pursuit of knowledge, becomes a powerful tool in this journey. Will we discover entirely new materials that enhance qubit stability, or will we develop innovative algorithms that allow quantum systems to self-correct in real time? Perhaps the answer lies in a combination of both, a harmony of invention that propels us toward the realization of functional quantum computers. The horizon is rich with potential, each breakthrough illuminating pathways previously obscured by uncertainty. As we continue to explore these frontiers, we find ourselves not just observers of a scientific revolution, but active participants in the unfolding narrative of quantum mechanics. Each moment, each discovery, invites us to engage with the mysteries of the universe, urging us to embrace the unknown with curiosity and wonder. The challenges of quantum superposition are formidable, yet they inspire a sense of excitement and anticipation for what lies ahead. In this vast landscape of possibility, we are reminded that the journey is as significant as the destination, with each step contributing to the grand tapestry of understanding that binds us to the universe. Amidst the intricate web of quantum mechanics, the challenges of achieving and maintaining superposition become ever more profound when we consider the stability of qubits in quantum computing. The quest to create qubits that can withstand the chaotic influences of their environment is akin to finding a treasure in a turbulent sea, where every wave threatens to disrupt the delicate balance of potentiality. One of the key aspects of this endeavor lies in understanding the impact of materials on qubit performance. The choice of materials is crucial, as they must exhibit specific properties that allow qubits to function optimally while minimizing decoherence. For instance, superconducting qubits, which utilize materials that conduct electricity, without resistance, can maintain coherence for a limited time, but they are still vulnerable to external noise. Researchers are experimenting with various alloys, semiconductors, and even exotic materials like graphene, which may offer enhanced properties, akin to discovering a new compass that guides us through the unpredictable waters of quantum states. Moreover, the design of qubit architectures is a fundamental consideration. Each architecture presents unique advantages and challenges. For example, while superconducting qubits are relatively straightforward to fabricate and manipulate, topological qubits promise greater resilience against decoherence due to their unique physical properties. This pursuit is reminiscent of a sculptor selecting the perfect stone for their masterpiece, where the inherent qualities of the material shape the final form of the artwork. Each qubit architecture serves as a canvas, awaiting the artist's touch to bring its potential to life. Another layer of complexity arises from the need for scalable quantum systems. As the demand for more powerful quantum computers grows, the challenge is not only to maintain superposition within individual qubits, but also to ensure that these qubits can interact coherently with one another. This interaction is vital for performing complex calculations. Picture a grand orchestra where each musician must not only play their part but also harmonize with the entire ensemble. If one musician falters, the symphony can quickly devolve into chaos. The same principle applies to qubits. Their interactions must be finely tuned to preserve coherence and maximize computational power. The field of quantum networking also presents intriguing possibilities for overcoming the challenges of superposition. By intertwining qubits across vast distances through quantum entanglement, researchers hope to create a network of quantum information that is both resilient and expansive. Imagine a city connected by luminous threads of energy, where each light represents a qubit that transcends the boundaries of classical limitations. This vision of quantum networks could enable robust communication systems and distributed quantum computing, unlocking new realms of possibility. As the scientific community continues to push boundaries, the exploration of novel error correction techniques offers a glimmer of hope. The resilience of quantum systems may be enhanced by leveraging entangled states, forming a protective shield against the disturbances that threaten coherence. Envision a network of interconnected bridges, each supporting and reinforcing the others, creating a structure that withstands the test of time and adversity. Ongoing research into error correction methods reveals the determination of scientists to cultivate stability in a landscape rife with uncertainty. With each discovery, the landscape of quantum superposition evolves, inviting us to imagine a future where we can harness its power fully. The challenges ahead are formidable, yet they are met with an unwavering spirit of inquiry and innovation. As we reflect on the ongoing research aimed at overcoming these obstacles, we are reminded of the resilience inherent in the pursuit of knowledge. Each step taken, each breakthrough achieved, is a testament to the human desire to explore the unknown and unlock the secrets of the universe. What lies beyond the horizon of our current understanding? Will the next generation of qubits emerge from the crucible of ingenuity? Or will new theoretical frameworks redefine our approach to quantum mechanics? The questions linger, inviting us to ponder the possibilities while we navigate this intricate dance of discovery. The challenges of quantum superposition may be daunting, but they also illuminate the path toward a deeper understanding of the cosmos, connecting us to the very fabric of existence itself. Chapter 9: Future Directions for Quantum Superposition Research. Emerging trends in quantum superposition studies illuminate a landscape rich with potential, inviting scientists and curious minds alike to explore the unknown. As researchers delve into the nuances of quantum mechanics, the boundaries of our understanding continue to expand. One of the most exciting trends is the exploration of quantum systems at macroscopic scales. Imagine a world where superposition is not merely confined to subatomic particles, but extends to larger entities, such as molecules, or even small mechanical systems. This shift could reveal insights into the very nature of reality, challenging our classical perceptions of the world. In recent years, experiments have demonstrated the possibility of observing quantum superposition in larger systems. For instance, researchers have successfully placed small mechanical oscillators into superposition states, effectively bridging the gap between the quantum and classical realms. This raises profound questions about the transition from quantum behavior to classical behavior. What does it mean for our understanding of reality when larger systems can exhibit traits traditionally reserved for particles? These inquiries not only captivate the imagination, but also pave the way for new discoveries in particle physics. The potential for new discoveries in particle physics is vast and exhilarating. Quantum superposition opens doors to previously unimaginable scenarios. For instance, as we investigate the properties of neutrinos, particles that rarely interact with matter, we may unlock secrets about the fundamental forces of nature. Neutrinos, elusive as shadows, can exist in a superposition of flavors, oscillating between types as they travel through space. This phenomenon hints at deeper connections within the universe, suggesting that our current models of particle physics could be just the tip of the iceberg. Imagine the possibility of harnessing these insights to explore particle interactions at energies previously thought unreachable. The Large Hadron Collider, an awe-inspiring testament to human ingenuity, could become a gateway to uncovering new particles and forces, revealing the intricate dance of the universe at its most fundamental level. The quest for knowledge has always driven humanity forward, and quantum superposition research promises to be at the forefront of this journey. Interdisciplinary approaches are also blossoming, combining quantum mechanics with fields such as biology, materials, science, and even philosophy. Picture a convergence of ideas where quantum biology explores the role of quantum effects in processes like photosynthesis and avian navigation. These investigations suggest that nature itself may be utilizing quantum phenomena to optimize efficiency in ways we are only beginning to understand. Could it be that the very essence of life is intertwined with the principles of quantum mechanics? As researchers collaborate across disciplines, they are uncovering profound insights that challenge traditional boundaries and expand our understanding of the natural world. Furthermore, the integration of quantum mechanics with advancements in artificial intelligence is poised to revolutionize multiple fields. Imagine leveraging quantum algorithms to enhance machine learning, allowing systems to process information at unprecedented speeds. The potential applications are vast, from optimizing complex systems to revolutionizing drug discovery processes. The marriage of these two realms could usher in a new era of understanding and capability, where quantum superposition fuels innovation in ways we have yet to envision. As we consider the impact of quantum research on societal advancements, the implications become increasingly clear. Quantum technologies are not just theoretical pursuits, they are rapidly taking shape in our daily lives. Quantum communication, for instance, promises to secure data transmission with unparalleled integrity. Imagine a world where messages are transmitted through the fabric of quantum entanglement, rendering them impervious to eavesdropping. This potential for secure communication could redefine privacy and security in an increasingly interconnected world. Moreover, advancements in quantum sensing hold the promise of revolutionizing fields such as geophysics and medicine. Picture sensors that can detect minute changes in gravitational fields, unlocking insights into the Earth's structure and behavior. In medicine, quantum sensors may lead to breakthroughs in imaging techniques, enhancing our ability to diagnose and treat diseases at earlier stages. The societal impact extends beyond technology. It also influences our philosophical understanding of existence. As we grapple with the implications of quantum mechanics, we are prompted to reconsider our perceptions of reality, causality, and interconnectedness. The interplay between observation and existence challenges us to reflect on our place within the universe. What does it mean for our understanding of consciousness when the act of observation plays such a crucial role in shaping reality? These inquiries not only fuel scientific exploration, but also ignite philosophical debates that transcend disciplinary boundaries. As we embark on this journey into the future of quantum superposition research, we are reminded of the words of Richard Feynman, who once remarked that the imagination of nature is far, far greater than the imagination of man. This sentiment encapsulates the essence of our endeavor. With each discovery, we peel back the layers of the universe, revealing a deeper understanding of the intricate dance of particles and forces that govern our existence. In this unfolding narrative, the future beckons with tantalizing possibilities. Quantum superposition, with its myriad implications, invites us to dream, to explore, and to embrace the unknown. As we stand on the precipice of discovery, we must ask ourselves, what wonders await just beyond the horizon? The landscape of quantum superposition is continually evolving, and as we explore future directions, it becomes evident that emerging trends are pointing toward groundbreaking discoveries. One such trend is the increasing collaboration among researchers across various disciplines. This interdisciplinary approach not only enhances our understanding of quantum mechanics, but also facilitates novel applications in diverse fields, such as engineering, biology, and even social sciences. Imagine physicists working alongside biologists to uncover the quantum mechanisms at play in photosynthesis, or engineers designing new materials inspired by quantum phenomena. This synergy could lead to innovations that were previously inconceivable, driving humanity's quest for knowledge to new heights. In particle physics, the potential for discovery is particularly electrifying. As researchers scrutinize the behavior of fundamental particles, they may unveil phenomena that challenge our current understanding of the universe. The exploration of dark matter and dark energy, two of the most elusive components of our cosmos, offers a tantalizing glimpse into this future. Could quantum superposition play a pivotal role in our understanding of these mysteries? As particles such as axions and WIMPs are investigated, understanding their properties through the lens of superposition could reshape our theories about the fabric of reality. These particles, if detected, might not only add depth to our existing models, but could also inform new theories that bridge gaps in our understanding of the universe's evolution. Furthermore, as we consider the implications of quantum superposition, we must contemplate its applications in quantum field theory, where the behavior of particles is described as fields permeating space and time. The development of quantum field theories has led to the formulation of the Standard Model, which encapsulates our understanding of the electromagnetic, weak, and strong forces. Yet this model remains incomplete, particularly in its treatment of gravity. What if the principles of superposition could provide insights into unifying these forces? The search for a theory of everything, one that reconciles quantum mechanics with general relativity, remains a formidable challenge. The exploration of quantum superposition within this context may yield the keys to unlocking a more profound understanding of the universe. Interdisciplinary approaches are not merely academic exercises. They are essential for the advancement of technology and societal progress. As quantum mechanics intersects with fields like artificial intelligence, we find ourselves at a crossroads of innovation. Imagine creating algorithms that leverage quantum superposition to process vast data sets in ways that classical systems cannot. The implications for fields such as climate modeling or personalized medicine are staggering. By harnessing the power of quantum computation, we could develop models that provide insights into complex systems, enabling us to tackle pressing global challenges with unprecedented efficiency. Moreover, the societal impact of quantum research extends into the realm of ethics and philosophy. As we advance our understanding of quantum superposition, we must also grapple with the ethical implications of these technologies. How do we ensure that advancements in quantum communication and sensing are used responsibly? The potential for surveillance and data security issues looms large, And as we embrace these technologies, we must do so with a conscientious approach. In the realm of quantum communication, the principles of entanglement and superposition promise to revolutionize how we transmit information. Envision a secure communication network where the act of eavesdropping disrupts the very transmission of information, alerting users to potential breaches. This level of security could redefine our notions of privacy in the digital age. As we implement these technologies, the collective responsibility to uphold ethical standards in their usage becomes paramount. Furthermore, the impact of quantum advancements on healthcare cannot be overstated. Picture a future where quantum sensors enable earlier detection of diseases, leading to more effective treatment options and improved patient outcomes. The marriage of quantum mechanics with medical imaging could yield techniques that visualize cellular processes in real time, potentially revolutionizing diagnostics. These advancements could not only enhance individual health, but also alleviate burdens on healthcare systems worldwide. As we ponder the future of quantum superposition research, we are reminded of the interconnectedness of knowledge across disciplines. The very fabric of our understanding is woven from insights that traverse boundaries, encouraging collaboration that fosters innovation. The pursuit of knowledge in quantum mechanics is not merely about unraveling the mysteries of the universe. It is about enhancing our collective well-being. The path forward is illuminated by the curiosity and ingenuity of scientists, researchers, and thinkers who dare to question the status quo. Each advancement in our understanding of quantum superposition brings us closer to a future where the boundaries of possibility are stretched, inviting us to explore realms beyond our current comprehension. What might we discover as we continue this journey? What marvels lie in wait, just beyond our grasp, ready to reshape our understanding of the universe and our place within it? The questions are as boundless as the possibilities, and the future is ripe with opportunity, beckoning us to venture further into the depths of quantum exploration. The horizon of quantum superposition research is painted with exhilarating possibilities, as emerging trends continue to surface and reshape our understanding of the universe. One particularly captivating area is the investigation into quantum superposition's implications for cosmology. Imagine the vastness of space, where the fabric of reality may be influenced by quantum phenomena at scales beyond our immediate perception. Theories connecting quantum mechanics with the dynamics of the cosmos invite scholars to ponder questions such as, how might quantum superposition elucidate the mysteries of black holes or the origins of the universe itself? In particular, the concept of quantum fluctuations, tiny temporary changes in energy that occur in otherwise empty space, may hold keys to understanding cosmic inflation. This phenomenon, theorized to have occurred shortly after the Big Bang, suggests that the universe expanded exponentially in a fraction of a second. Could these fluctuations, which exist in a superposition of states, have seeded the formation of galaxies and structures we observe today? The marriage of quantum mechanics with cosmology encourages a breathtaking exploration into the origins and evolution of our universe. As we delve into particle physics, we find that the pursuit of new discoveries is not limited to theoretical frameworks. The experimental frontiers are bustling with activity as international collaborations aim to push the boundaries of what we know. The search for new particles, particularly those that could account for the mysteries of dark matter, is a driving force in modern physics. Researchers are utilizing advanced detectors and collider experiments to probe the depths of superposition and entangled states. As they sift through data, they seek anomalies that could signal the presence of new physics, potentially transforming our understanding of the fundamental forces that govern the universe. The allure of discovering new particles often brings to mind the pioneering work of figures like Maria Goeppert-Mayer, who, alongside her contemporaries, contributed to the development of the nuclear shell model. Her journey was marked by tenacity and intellectual curiosity, qualities that continue to inspire the next generation of physicists. The impact of her work illustrates how each discovery in particle physics can spark further inquiry, leading to questions that transcend the immediate findings. What new theories might emerge as we uncover the secrets of superposition and its role in the universe? Interdisciplinary approaches are also flourishing, creating a rich dialogue between quantum mechanics and fields like neuroscience. Imagine a scenario where the principles of quantum superposition might inform our understanding of consciousness itself. Could the enigmatic processes of the brain, thoughts, perceptions, and memories be influenced by quantum phenomena? Researchers have begun to explore the idea that quantum effects could play a role in neural processes, leading to groundbreaking insights into how we perceive reality. This intersection invites a profound inquiry. What if our very consciousness is entangled with the quantum world, shaping our experiences in ways we have yet to fully comprehend? Additionally, the implications of quantum superposition extend into the realm of environmental science. The quest for sustainable energy solutions may find inspiration in quantum phenomena as researchers investigate the efficiency of energy transfer in natural systems. Imagine harnessing the principles of superposition to develop more effective solar cells or catalysis processes. The efficiency observed in photosynthesis, where light energy is converted to chemical energy with remarkable precision, exemplifies the potential for quantum mechanics to inform advancements in renewable energy technologies. Could we unlock the secrets of nature's efficiency to create sustainable solutions for the future? As we reflect on the societal advancements stemming from quantum research, the potential for educational reform emerges as a key consideration. The complexities of quantum mechanics, once deemed esoteric, are gradually finding their way into educational curricula. Picture classrooms where students are introduced to concepts of superposition and entanglement through engaging experiments and simulations. This shift not only fosters a deeper understanding of the universe, but also cultivates critical thinking and creativity among young learners. How might this new wave of education inspire future generations to tackle challenges we cannot yet envision? Moreover, the ethical ramifications of quantum technologies compel us to engage in thoughtful discourse. As advancements in quantum computing and communication unfold, we must grapple with the implications for privacy and security in a digital world. The potential for quantum encryption to revolutionize data security is tantalizing, yet it urges us to consider the responsibilities that accompany such power. How do we navigate the delicate balance between innovation and ethical considerations, ensuring that the benefits of quantum research are shared equitably across society? In this unfolding narrative of quantum superposition research, the future is illuminated by the collective curiosity and dedication of a vibrant community of scientists and thinkers. With each discovery, we inch closer to revealing the intricate connections that bind the cosmos and the fundamental laws that govern our existence. As we ponder the mysteries that lie ahead, we are beckoned to embrace the journey of exploration, where questions abound and possibilities stretch beyond the confines of our imagination. What marvels await us as we continue to unravel the profound implications of quantum superposition? The answers remain elusive, shimmering on the horizon, inviting us to explore further. Chapter 10. The Significance of Quantum Superposition Today. The concept of quantum superposition stands as a cornerstone in modern science, illuminating pathways into the very fabric of reality. As we reflect on its significance, we find that it not only reshapes our understanding of the universe, but also serves as a beacon guiding us toward future innovations. Superposition invites us to imagine a realm where particles exist in multiple states, a notion that challenges our conventional views and expands the horizons of scientific inquiry. At the heart of quantum mechanics lies the idea that particles are not confined to a single existence. Instead, they embody a multitude of possibilities, each waiting to be revealed. This understanding has been pivotal in advancing fields such as quantum computing, where the ability of qubits to exist in superposition enables exponential increases in processing power. Imagine an ocean of potential outcomes, with each wave representing a different solution to a complex problem, all explored simultaneously. Such a vivid imagery illustrates the profound implications of superposition, allowing scientists and engineers to tackle challenges that were once deemed insurmountable. As we ponder the role of superposition, we must consider its impact on our understanding of the universe itself. It compels us to rethink the nature of reality, suggesting that the universe is a tapestry of interwoven possibilities rather than a static entity. The late physicist Richard Feynman once remarked that the universe is not only queerer than we suppose, but queerer than we can suppose. This sentiment encapsulates the essence of superposition, inviting us to embrace the mystery of the unknown. The potential implications of superposition extend far beyond theoretical musings. In recent years, we have witnessed a surge of interest in how quantum phenomena can be harnessed to revolutionize technology and society. The advent of quantum computing heralds a new era in computational power, but the applications of superposition do not end there. Quantum sensors, for instance, utilize the principles of superposition to achieve unprecedented sensitivity in measurements, paving the way for advancements in fields ranging from medical imaging to environmental monitoring. Imagine a device so finely tuned that it can detect minute changes in gravitational fields, offering insights into the very fabric of space-time. In addition to technology, the implications of superposition resonate within the fabric of our society. As quantum principles permeate various fields, a growing public interest in quantum mechanics emerges. Educational initiatives are blossoming, aiming to demystify the complexities of quantum theory and make it accessible to a broader audience. Imagine classrooms filled with eager minds, exploring the wonders of superposition and entanglement, fostering a new generation of thinkers who will carry the torch of inquiry into the future. The fascination with quantum mechanics is not merely academic. It ignites a spark of curiosity that transcends disciplines, inspiring artists, philosophers, and scientists alike. As we engage with the principles of superposition, we find ourselves at the intersection of science and imagination. This interplay encourages creative exploration, prompting questions that extend beyond the laboratory and into the realms of philosophy and ethics. As we continue to explore the significance of quantum superposition today, we must also acknowledge the challenges that accompany such profound discoveries. The delicate nature of quantum states poses obstacles that researchers must navigate, requiring innovative approaches to maintain superposition in experimental contexts. Yet, it is within these challenges that the promise of groundbreaking discoveries lies. By confronting the intricacies of quantum behavior, scientists are propelled into new territories of understanding, uncovering phenomena that challenge the very foundations of classical physics. The allure of quantum superposition is not solely within its scientific applications. It also serves as a reminder of the beauty inherent in the mysteries of the universe. The notion that particles can exist in multiple states simultaneously evokes a sense of wonder, inviting us to reflect on the nature of existence itself. As we contemplate the universe's intricacies, we are reminded of the words of the physicist Niels Bohr, who remarked, "We are all agreed that your theory is crazy. The question that divides us is whether it is crazy enough to be true." This ongoing dialogue about the significance of quantum superposition reflects a growing appreciation for the interconnectedness of knowledge. As the boundaries between disciplines blur, collaboration among scientists, educators, and the public becomes essential. The quest for understanding is not confined to laboratories. It extends into the hearts and minds of individuals who seek to comprehend the universe's enigmatic nature. As we embrace the potential of quantum superposition, we are encouraged to envision a future where the mysteries of the universe are not only uncovered, but celebrated. The journey into the quantum realm is one of exploration and discovery, a path that invites us to question, to dream, and to imagine the possibilities that lie ahead. In this ever-evolving landscape, the significance of superposition resonates deeply, inviting us to participate in the unfolding narrative of science and humanity. The ongoing public interest in quantum mechanics reflects a collective yearning to grasp the profound implications of superposition. As we engage with this captivating subject, we find ourselves drawn into discussions that transcend traditional boundaries. The questions we ask today will shape the discoveries of tomorrow, propelling us into a future where the mysteries of the universe are not merely observed, but experienced. In this interconnected world, the significance of quantum superposition today serves as a catalyst for innovation, collaboration, and exploration. It invites us to ponder the very nature of existence while inspiring us to envision a future where the wonders of quantum mechanics become integral to our daily lives. As we stand on the threshold of this new frontier, we are reminded that the journey of discovery is as important as the destination itself, urging us to remain curious and open to the extraordinary possibilities that await us. As we immerse ourselves in the significance of quantum superposition today, we begin to see its profound implications ripple through our understanding of the universe. This remarkable principle not only reshapes the landscape of modern science, but also encourages a reimagining of our place within the cosmos. It is a reminder that the universe is a playground of probabilities, where outcomes exist in a delicate balance of potential until they are observed or measured. Consider the remarkable physicist Erwin Schrödinger, who famously illustrated the strange nature of superposition with his thought experiment involving a cat that is both alive and dead until observed. This paradox challenges our intuitions and beckons us to confront the complexities of reality. What if we too exist in a state of potential, shaped by observations and our interactions with the world around us? This notion encourages us to reflect on our roles as both observers and participants in the unfolding narrative of existence. The implications of quantum superposition extend well beyond the confines of academic inquiry. As technology continues to evolve, the ideas rooted in quantum mechanics are beginning to manifest in tangible innovations that could revolutionize our daily lives. From quantum computing to advanced cryptography, the promise of harnessing superposition is being realized in exciting new ways. Imagine a future where quantum computers perform calculations in the blink of an eye, solving problems that would take classical computers centuries to unravel. This potential for accelerated problem solving could have far-reaching consequences, from optimizing transportation systems to enhancing artificial intelligence. Moreover, the intersection of quantum superposition with artificial intelligence presents a fascinating frontier. The ability of quantum computers to analyze vast datasets with unprecedented speed could lead to groundbreaking advancements in machine learning and data processing. Picture algorithms that learn and adapt in real time, utilizing the power of superposition to explore multiple solutions at once. This convergence of quantum mechanics and computational technology could redefine our understanding of intelligence and the boundaries of machine learning. As we delve deeper into the societal impact of quantum superposition, we recognize that its effects ripple through various fields, inspiring new ways of thinking and problem solving. The principles of superposition challenge us to embrace uncertainty and complexity, fostering a mindset that is essential in an increasingly interconnected world. In a society that often seeks clear-cut answers, quantum mechanics urges us to appreciate the beauty of ambiguity and the multitude of possibilities inherent in every situation. Public interest in quantum mechanics is surging, driven by a collective desire to understand the mysteries that lie at the heart of our reality. Science communication initiatives are emerging, aiming to bridge the gap between complex theories and everyday understanding. Imagine a world where students engage with quantum concepts not just in classrooms, but through interactive exhibits and community discussions, fostering a culture of curiosity and inquiry. This educational momentum holds the potential to cultivate a new generation of thinkers who are not only well-versed in scientific principles, but also equipped to tackle the challenges of tomorrow. The allure of quantum mechanics is not confined to scientists alone. It resonates with artists, writers, and thinkers across disciplines. The fluidity of superposition inspires creative exploration, inviting individuals to envision new narratives that intertwine science and art. Artists draw upon the dynamic nature of quantum states to express the complexities of existence, while writers weave stories that reflect the profound interconnectedness of all things. This cross-pollination of ideas enriches our cultural landscape, illustrating how science can inspire creativity and vice versa. As we reflect on the challenges and opportunities presented by quantum superposition, we must remain cognizant of the ethical implications that accompany these advancements. The extraordinary capabilities of quantum technologies raise questions about privacy, security, and the potential for misuse. How do we ensure that the power of these innovations is harnessed for the greater good? This inquiry calls for a collaborative effort among scientists, ethicists, and policymakers to navigate the uncharted waters of quantum applications responsibly. In this complex tapestry of knowledge, the significance of quantum superposition today serves as a beacon, guiding us toward a future filled with possibilities. It encourages us to remain curious, to question, and to explore the depths of our understanding. As we stand on the precipice of discovery, we must embrace the unknown, recognizing that the journey into the quantum realm is not just about uncovering facts, but also about celebrating the wonder of existence itself. With each new revelation in quantum mechanics, we inch closer to comprehending the universe's intricate design. The stories of scientists who have paved the way, from Planck to Feynman, inspire us to delve into the enigmatic world of quantum physics. Their contributions remind us that the pursuit of knowledge is a shared endeavor, one that transcends individual achievements and fosters a collective understanding of the cosmos. As we move forward, let us carry the spirit of inquiry in our hearts, embracing the complexities of quantum superposition and the myriad possibilities it presents. The ongoing exploration of these principles is a testament to our innate curiosity and a reminder that the universe is filled with mysteries waiting to be unraveled. Each question we ask, each discovery we make, brings us closer to understanding the profound significance of our existence in a world shaped by the interplay of superpositions.